Hello and welcome to this last session on the last day of grade LPSC. And I am one of the session chairs, Lindsay McHenry, and I'd like to introduce my co-chair here, Al Emran, and our moderator over here, Robert Platt. And so I think by this point you know the rules and you know what to expect for a session, but I'm going to go through that anyway, so bear with me. So welcome to our in-person and our online remote audience. And this session is divided into 3 blocks of 4 talks, 10 minutes each. No questions between talks, but of course we have a nice discussion section after each block of 4 talks. A reminder for our in-person audience to mute your cell phones so we don't interrupt the speakers. And if you have a question during one of the question and answers after each block, please walk up to the microphone to give that question and make sure to identify yourself with your name and affiliation when you do so. If you are joining us on the remote, so if you're here on the Zoom, then you will submit your written questions versus the Q&A forum function there. And the moderator or one of the co-chairs will read those during the discussion section. But even if you are an online participant, please still identify yourself by name and affiliation so we can read that out with your question. And let's see. Okay, I haven't seen any really fiery debates yet at this conference, but just in case, make sure to keep the discussions civil and appropriate, concentrating on the science rather than the person up here. And so we'll use we'll use the microphones here during the Q&A for in-room participants. Of course, the Q&A function for the Zoom. And if you want to keep these conversations going following the session, then there is a Slack channel for the conference where you can do that. Just a reminder that official LPSC ambassadors are going to be posting highlights across this conference. So if you do not want your presentation to be, or highlights of your presentation to be shared, so if it's under embargo or something, it's your responsibility to let them know, to announce that you do not want anyone to be reporting on it. No photography or streaming during the session. Yep. And all of the sessions are going to be recorded and available to people who've registered for the conference for 30 days following the conference ends. So if you miss something, if you have to take a potty break and you miss a talk, you can always watch the recorded version of it for the next month. And I think we got 1 minute to go now. Oh yeah. And if you are a speaker, if you can get mic'd up quickly before your during the preceding talk, so we can do a quick change between talks, that would be awesome. Oh, and it's 8:25. So our first speaker would like to come up.
So the first speaker is Alexandra Hearn, and the topic is characterization of thermophysical properties of rock units throughout Curiosity's mission at Gale Crater.
Great, good morning. Thank you to everyone who's here on this bright and early Friday morning of LPSC. Appreciate that. So basically the goal of my work is probably a little bit different than a lot of people in this session. And what I'm interested in is characterizing the physical properties of rocks and sediment throughout the strat column that we've observed at Gale with Curiosity. To do this, I have to isolate individual thermal inertia values of rocks and sediment in order to properly characterize them. And then using lab results from Marcia Presley and Phil Christensen, and then from work that I did that came out last year, I can then tie those physical or those thermal inertia values to actual meaningful geological properties. So in the interest of time, I have to do a very quick thermal inertia review. Basically, we know thermal inertia is a function of the thermal conductivity, bulk density, and specific heat of a material. We can't often know these properties of rocks just by looking at them on Mars. But thermal inertia is a good indicator of physical properties other than like bulk density. It gives us a clue of cementation or degree of induration, maybe degree of fracturing in rocks. We get thermal inertia by using thermal models and inputting surface brightness temperatures from the rover. And you can see I just a sample plot here. We have unique curve shapes depending on the thermal inertia values of the material, and we can then back out physical properties that way. So how do we get these surface brightness temperatures? On Curiosity, we are fortunate to be collecting REMS data frequently so that we can fill in these full diurnal temperature patterns. So REMS is located on Curiosity's mast and is basically constantly throughout the mission been measuring surface temperatures in these little oval footprints. So we get these brightness temperatures from radiance data over the entire footprint, and then we get these unique temperature curves that are related to the thermal properties of the materials in the oval. But as you can see, those ovals are full of multiple materials. And so in our thermal modeling, we have to take that into account among other things. And unfortunately, I don't have the time to go through all of the model considerations that we've done, but I want to highlight a few. So we're using the KRC thermal model, which was developed by Hugh Kiefer and is described in his 2013 JGR paper. And up in this top corner, you can see that we are accounting for these complex surfaces that have vertical layering in the shallow subsurface. We have kind of these patchy mixes of rock and sediment. So that kind of psychedelic looking image is I've had to kind of map out the rock and sediment proportions so that I can more accurately model these things. But we're also interested, we collect like rover location, geographic and temporal data to put into the model. We also have to worry about atmospheric dust opacity, which we retrieve from work done by Mark Lemon and others. From Curiosity observations, the dust opacity affects our ability to get accurate surface brightness temperatures, so we need to know this. And then lastly, our GTS footprint is often on a sloped surface, and this affects how much solar energy that part of the surface is receiving. So we've been using methods developed by Kevin Lewis to using NavCam images to get slope, tilt angles, and azimuths. So Curiosity has been collecting this data throughout the mission, but we can't just anytime it's sitting anywhere use these methods. So basically we have some criteria that I kind of have to speed through, but we need at least 5 sols worth of data we found in order to build a full diurnal curve. And so we're trying to get at least 50 of the 96 points. So we are using these in 15-minute bins, and we want to have as much of the curve filled in as possible for our model fits. We also have to worry about atmospheric dust opacity, like I said. So we can't really do this when we're in dust storms or high dust times. And then lastly, after we've done all of these thermal models, we have to actually make sure that our results make sense. So for instance, just as a quick example, if we have a GTS field of view that is mostly exposed bedrock, and the only fits we can get indicate that its thermal inertia is related to meters thick dust, then we're not maybe getting the best temperature data, or we're just not accurately fitting it with our models. So we throw some of those out. And I just want to highlight this really quickly. So the way that we're actually getting these thermal inertia values into something important and useful and relevant to geologists is through lab work. So I already kind of briefly mentioned Marcia Presley and Phil Christensen. They had a really important study in the 90s where they were able to measure sediment grain size and tie that to thermal conductivity at Mars pressures. Well, last year we published a similar thing, but for rocks, which had not been done. So we have this really great Mars relevant sample suite of igneous and sedimentary rocks. We have all of these properties that we measured so that we can get this, really good picture of what these samples are like. And it was our attempt to directly quantitatively link thermal inertia and thermal conductivity with bulk density and porosity, because we already know bulk density is part of the equation, but we usually don't know the thermal conductivity or the specific heat capacity of these rocks and sediments. So just an easier way to transition that. So I just want to call that out. This was a PDART award, and the data set is available along with the 2024 Icarus paper. All right, so just really quickly, with the results. So far in our 82 locations, we've seen an array of sediment thermal inertia values. Now, many of you may not care or really understand deeply what these numbers mean, and that makes total sense. So what I've done here is I have labeled these based on the Wentworth grain size, so you have an idea. So we're seeing grain sizes from 15 microns to about 1.1 millimeters throughout the mission. And this was just, we're really interested in the rocks, but we wanted to know kind of what was going on with the sediment as well. And one thing we found that is interesting is that Vera Ribbon Ridge seems to have our biggest grain sizes. We've kind of just been through these results, so we're kind of trying to figure out what some of this actually now means, but that was a finding that we have encountered. So the rock thermal inertia is pretty varied. So in this case, instead, I have thermal inertia on the x-axis, and I have the stratigraphy or elevation throughout the crater on the y-axis. These values might be surprising to you, that we're seeing thermal inertias both this high and this low of rocks. If you have done other types of thermal inertia studies, this may surprise you. I want to call attention to the fact that we have isolated the rock components away from the sediment. So oftentimes, if you're looking at a sediment-covered rock, then you start to get a lowering of the thermal inertia from that influence of the sediment. But this way, we're actually only looking at the rock. Additionally, we find this to be consistent with the laboratory measurements that we did of mudstones and sandstones. We see this really, really wide range based on cementation, porosity, those kinds of things. Now, based on our lab data, we're seeing bulk densities of a pretty big range and porosities of a pretty big range as well. Now, we're not necessarily claiming that these are absolutely the bulk density and porosity values, but what we're saying is, based on the laboratory data that we did and the values that we are getting as our best fit thermal inertia values for these rocks, this is kind of the ballpark that we're working in. Since obviously the strat column is big now and we can't see the whole thing, I've kind of just broken this down into the big groups and formations that we've encountered thus far with the rover. And what's interesting is that we see our highest thermal inertias at the Stimson every time we've visited it. Just kind of as a summary, though, the lowest thermal inertias that we seem to see so far are in mudstones. So in the Bradbury group, in the Carolyn Shoemaker formation, we're seeing these low thermal inertia values, which we say we're still kind of processing why this may be the case. Is it because these rocks are really fractured? So the bulk rock itself may not have this low of a thermal inertia, but the intense fracturing has caused that open space. Or are these rocks more friable than maybe we think? Not sure yet. Stay tuned. And again, our highest thermal inertia values are seen in the Stimson and other aeolian sandstones. This is consistent with the well-cemented nature that we have observed at the Stimson. And these are kind of the values that translate in porosity and bulk density. Skip that one. So basically, I've kind of been over our conclusions really quickly, but it's really important that we are able to isolate these rock properties thermally, because then we can kind of get a better idea of what the rock is doing without the influence of sediment. And just looking forward, we're really excited to see the host rocks of the boxwork structures thermophysically to kind of get an idea of what's going on and why these features have formed in that rock. So thank you.
Thank you very much. 4 seconds to spare.
Our next speaker, Sarah Simpson, and title X-ray amorphous material in Grail crater, Mars observation, major trend and implication for paleoenvironmental condition.
Okay, good morning, and thank you for showing up. So this morning I'm going to be talking about the enigmatic X-ray amorphous materials that we find in Gale Crater. And I want to start off by thanking my co-authors. This has been a hugely collaborative effort across multiple instrument teams, and I could not do this without them. So thank you to them. Okay, so just a really quick overview for folks who are unfamiliar. This is a really simplified geologic map showing the section of Curiosity's traverse that I'm going to be covering. So this is a really basic mineralogy map. So you can see the hematite-rich Vera Rubin Ridge up here. And we also have the clay-rich Glen Torridon region in blue. And this little sliver of yellow is the clay sulfate transitional region, and I'm going to end in the sulfate unit. And each one of these white dots represents a sample that Curiosity drilled. So yeah, I'm going to be starting at Aberlady, which is the first drill sample that Curiosity collected or analyzed in the smectite-rich Glen Torridon region. And I'm going to be ending at Sequoia, which is in the sulfate unit. So this is our position as of last week down here with the smiley face right there. Yeah, so the reason that I've chosen this section of the traverse is that we believe, and I think most folks agree, that this section records a major environmental change, and that is reflected in the geology and the mineralogy of this section of the traverse. So I mentioned that Glen Torridon is the clay-rich region. So this is primarily a subaqueous depositional environment, and it's very clay-rich. And then when we moved into the transitional units, we began to lose those phyllosilicates, and then we completely lost them in the sulfate unit. So we want to know, does the X-ray amorphous material that we find in Gale Crater also record these changes, and can we compare the amorphous component, the composition and the abundance, to some of the trends that we're seeing in the mineralogy and the depositional environment to get a better picture of what's going on in Gale Crater and I guess Mars as a whole. So for folks who are unfamiliar with amorphous materials, every single sample that we have analyzed in Gale Crater by the Chemin XRD contains an X-ray amorphous component, and it's not a small amount either. This ranges sometimes up to 70 weight %. So this is a huge part of the sample that we're missing information on often. And this is what it looks like for folks who do XRD. The amorphous component shows up as this amorphous hump, background hump, and it's usually between 25 and 30 degrees 2 theta. And when I say amorphous, I mean that it does not contain long-range crystallinity. So this is like a really basic Geo 101 definition. It does not fit the traditional definition of a mineral. So this material could contain short-range orders, so something like along the lines of like allophane, which is considered a mineraloid, and less likely, I think, it could be actually something truly amorphous, like a pristine, totally unaltered glass. But I'm not totally convinced that that is present because it's metastable. So yeah, so this material has been sitting around potentially for billions of years, and this is in the an image from the Amapari marker band outcrop in the sulfate unit. And even when we thought that things were drying up, we came across this really strange outcrop, and there's a lot of papers that might have been published already on this. But it's just really begs the question: why do we have so much amorphous material in an area that we have all these dynamic changes? And why is there so much of it on Mars as a whole? And we've also seen amorphous materials that are inferred from spectral data sets as well. So why is it all over Mars, and why is there so much of it in Gale, and what is it made out of? So I'm going to try really quickly in the time that I have to answer the following questions. Is the amorphous component, is the abundance changing across Curiosity's traverse as we ascend Mount Sharp, and why? What is it made out of, just generally? And are there any correlations with lithology, depositional environment, mineralogy that we can draw from this? So this is a really, really brief overview of our methods. We basically, how do we derive the amorphous component composition and abundance? We use Chemin XRD, which gives us quantitative and qualitative mineralogy, crystal chemistry in an amorphous abundance. We also use APXS data, which gives us the bulk sample composition. And we also work really closely with SAM EGA, which gives us information on the volatile content as well, such as the water from the clay minerals. And then this gets fed into a mass balance calculation, where we basically subtract the mineralogy and the mineral chemistry from the bulk sample composition. And again, this does not come without errors and assumptions, and I've been very clear about that with folks I've spoken to. And the remaining excess from this is what is inferred as the amorphous component. So the first question I said I would address is the amorphous abundance changing? And the answer is yes, for the most part. So this is what the amorphous abundance looks like, and this is what the errors look like as well. So you can see in Glentoran, we have around 35 weight%, and as we move into the sulfate transitional region, it's around 50, and then it looks like it's starting to increase maybe less as dramatically as from the smectite to the sulfate transitional region, and it's about 57 weight%. So something that I want to point out that I think is really important and I keep coming back to in this presentation in the paper that I'm writing is that where we see the clays start decreasing are in the transitional unit and then they disappear around Pontours and Maria Gordon, I think this is really important and I think it's a major change in the traverse that is reflected in the amorphous component as well. And we also see this in the mineralogy. So you can see once the clays disappear, we see the amorphous abundance increasing and then they haven't come back in the bedrock yet. We have found smectites in a recent sample, but it was not in the bedrock. So I want to again emphasize that this shift right here is also occurs where there is where we move from primarily subaqueous to subaerial depositional environment. And I think what this is telling us is that the amorphous material, whether it's a primary or secondary phase, it is preserving. Regardless of what it's made of, it is increasing and it's persisting. So it's still there. So I think this is also, the loss of clays is also an indicator of relatively lower water rock ratio as well. So the next thing I want to talk about, and I'm going to breeze through this and it's really simplified, is what is it made out of? So the amorphous component is primarily made out of SiO2, SO3, iron, and magnesium. So there are other oxides, anything that APXS measures, we can also get in the amorphous component, but they are far less abundant or the errors are often really difficult to work with. So the first thing I want to point out is that the bulk forming amorphous material components are SiO2 and SO3, and they are anti-correlated. They are consistently anti-correlated across all of these regions. Just a couple of notable samples. Canaima had the largest amorphous sulfate component, that was about 15 weight%, and Zechstein is really hard to work with. Zechstein was a sample we analyzed that was a really big chunky gypsum vein, and it's usually an outlier in almost all of my data sets, so I try to ignore it for the most part. And the relationship between the SiO2, SO3, magnesium, and iron changes. It does change across these regions along with the mineralogy. So the first thing I want to point out is the relationship between silica and iron. So in the Glentoran region, they appear to suggest that they are anti-correlated. And then again, where we lose these clays around here, this relationship changes and they appear to be positively correlated and the patterns sort of follow each other. So I think that this trend reversal is reflected, or is I guess the exception to this is the lower Glentoran samples, so that's something I need to look at as well. And I think that this happens here around when we lose the clay minerals. And I think, again, this is a shift to a cold and dry environment. And along with, if we're not forming our iron-rich smectites, our smectites and Gale Crater are very, very iron-rich nontronites. And I think a lot of that iron is getting pushed into the amorphous component. And also, my supervisor, Liz Rampey, has done a lot of analog work on sediments in proglacial environments and also finds a lot of iron silica rich amorphous phases. So this, I think, is a reflection of lower water rock ratio, generally drier, but not completely dry environments, favor amorphous iron and silica phases. And whether these are one phase together or separate is something that we're working on. So the other thing is it's possible that this shift to more iron and silica rich amorphous material could also be reflective of palagonitic or glassy phases. And Steve Chipra is doing a lot of work on modeling those as well. The other relationship that I wanted to point out is the amorphous sulfate. The Glentoran and clay-rich region is likely dominated by amorphous iron sulfate. And then again, I think that this shift changes, and we can see this in a lot of the Chemin data as well. It starts to become more amorphous magnesium sulfate as we begin to dry up in this region. And I think the largest sample with the most amorphous sulfate is Canaima. So this again happens when we see this trend reversal with iron and silica as well. So I think that this is really telling us something. So again, this is where we lose the clays and the samples start to become more magnesium sulfate rich. So Canaima had the largest amount of amorphous magnesium sulfate, which was around 24 weight%. And the other thing that I wanted to point out as well is that we've been looking at a lot of SAM EGA data, and it agrees with most of our interpretations as well. So right here you see amorphous iron sulfate, amorphous magnesium sulfate starts to increase, and I have got to go through my conclusions. Yeah, so in conclusion, amorphous material is increasing. It does have some really interesting chemical relationships, and I think that is reflected in the loss of clay minerals as our environment is changing, and we still have a lot of work to do. And I am sorry that I ran out of time. Thank you.
Thank you. So our next speaker is Ashley Murphy, and the title is Partially Resolved Complex Organic Matter Detected in an Ancient River Valley in Jezero Crater, Mars.
Thank you. Yeah, we're switching over to Jezero Crater now, and I'll be speaking about our results at the Bright Angel outcrop. So I'll be speaking about the Sherlock results today, and just as a reminder, Sherlock is a deep ultraviolet Raman and fluorescence spectrometer, and we have two imagers, Watson, which is basically our version of Molly, which is on the Curiosity rover, and our ACI, which also provides us context, and this is where we collect our spectra from. This is Jezero Crater, and if we zoom into the white outline here, we see Neret Vivalis, the inlet channel, and the Bright Angel outcrop, which is located on the northern side. Sherlock analyzed 4 targets across 3 rocks in this area, and abrasions on the Walhalla Glades target, the Apollo Temple target, and the Steamboat Mountain target. For the Apollo Temple abrasion, we also analyzed the natural surface of the rock, which is called Chiava Falls, and we later took a rock core of this. If we take a look at our Watsons here, these 4 larger images, we can see that these are predominantly fine-grained mudstones. Some of the grains are so fine that they're below our resolution for our imagers. We do see these coarser grained in Steamboat Mountain up in the corner, these coarser grained olivines that are set in a finer grain matrix. And for the natural surface Chiava Falls, there's these really coarse grains veins cutting through it. And even after we abrade it in Apollo Temple, we can still see those veins. The panel on the side are colorized ACIs, and those yellow boxes mark where we placed Sherlock. And each of those 1-by-1 detail scans that we performed, there's 100 points analyzed in each. If we take a look at the average of that spectrum here, this waterfall plot shows all of the targets. And one of the things that stands out, it's at the top, it's Steamboat Mountain. We have a very strong sulfate signal and it's hydrated. There's a hydrated stretching mode over here in this higher wave number region. So this is consistent with the basanite mineral. But we don't see hydration in any of the other samples. But we do see this really broad mineral feature, which is consistent with silicate. And in the Apollo Temple, we were able to pull out some sulfate and carbonate signals within there that I'll show in the next slides. We also saw a feature around 1600 that's marked here as the G band, and this is consistent with organic carbon. Down below here, we analyzed our algan calibration target, and this was to kind of serve as a negative control because we don't expect to see an organic carbon signal here. And the very lowest one in gray, this is our instrument optical background signal. So if we zoom into the G-band area and look at the panel B, we fit that it's kind of hard to see here, but there's a slight hump in that region in our background signal. So we fit that here in the gray line, and then we deconvolved it from all of our peaks here to make sure we were just looking at the G-band, which is shown after we deconvolve that, it's in the black here. Again, we don't see anything in our algan target. And if we look across these G-band signals or organic carbon signals, we see that they vary in their peak position and in their bandwidth, which is the full width at the half max here. And if we look at our hydration bending mode that's in this basanite, we see that it's much more narrow than those G-bands, and it's at a higher wave number. So we wanted to see if we could dig out any connections between spectral and textural data. So we did this by using an algorithm. For the Steamboat Mountain here, there was 100 points in this map, and we ranked the most intense 15%, which in this case is 15 points that are marked by these hollow circles here. This represents our annulus laser spot. And we rank this off of this hydration stretching mode. So that average spectra that I showed in the previous slide is in the green, and our comparison in the gray are represented from these spots. And this is showing that it pulls out a more intense hydration features here and the sulfate feature compared to the average. And it's correlated to these wider rims. So this is showing us that we can pull out some textural information to see where that sulfate is within the map. So we did the same thing on that natural surface of Chiaralba Falls, but this time we ranked the spectra based on the most intense G bands. And what we found was there doesn't appear to be really any change in the mineralogy with these higher G bands or the more intense G bands. And it's just kind of scattered throughout the matrix. But this was quite a bit out of focus or away from our ideal focus. We were a bit too close to the targets. That's why the spectra is pretty noisy here. So there could be some sort of association with texture that we just couldn't pick up because we were a bit out of focus. We did the same thing for the abrasion of that rock, Apollo Temple. And what we found across these is that it pulled out this carbonate peak here. So this new 1 mode is the most intense mode for carbonate. So we were able to pull out an association of the G band to the carbonate. But when we look across the texture, these points just seem kind of scattered about and they're not really associated with anything in particular. We also pulled out a bit of a sulfate signal using the same process. So this is a bit of a stronger sulfate signal compared to the average, but the G band associated with that just looks like the average G band roughly throughout the whole spectrum here. And again, it's just kind of scattered throughout the rock and it's not really associated with any particular texture. And finally, we did it for Walhalla Glades, the same thing. We looked at the most intense G band points, and what we found was they were associated with the lighter texture of the rock and not these darker grains. So the next thing we did was compare the Bright Angel targets, the G band peak center and the bandwidth to reference samples that we had. So the shapes here, if it's a star, it's Sherlock. If it's any of these other shapes, it's a Sherlock analog where we collected reference data from. The colors here represent the different type of samples we used, and these error bars are errors on our peak fit uncertainty. So we use various meteorites such as carbonaceous chondrites, Martian meteorites, urolite and iron meteorites, terrestrial fossils that span from plant, fish to microbial fossils. They vary in lithology, they vary in geologic alteration and time, geologic time. And we have coal samples too that vary by rank. And some synthetic samples like a graphite, and then we have insoluble organic matter. And we're calling this a terrestrial terrestrial abiotic carbon, and it's a xenolith from Svalbard here. Over here, the spectra is just examples from at least one of these types of reference materials that we use just to give you an idea of what these peaks look like. And the main takeaway here is we found that all of the graphite mineral samples and any sample that had graphitized carbon within it was a relatively narrow bandwidth and plots in these lower wave numbers here. So even though our error bars are quite large on some of these Sherlock Bright Angel, these black stars here, they don't overlap in this area, which means it's not consistent with the mineral graphite or anything graphitized. It's some sort of amorphous carbon that we're looking at. However, it overlaps with so many different terrestrial and meteorite samples that it's hard to pull anything else out from this sample. So in conclusion, Bright Angel is very unique, and this is the first outcrop and area where Sherlock's analyzed that we've picked up numerous G-band signals across various targets or multiple targets. And it's also the first detection that we've had of organic carbon on the surface from that surface rock target called Chiaralba Falls. So it doesn't appear to be consistent with graphite, but there's not much else we can say about the source or the alteration of it using just the Raman signal alone. So with that, I just want to thank you. I just want to acknowledge my funding and thank you.
So our next speaker is Jade Gomelas, and talking about using BIS-IR and Raman to study iron serpentine, Hisingerite supporting superchem search for alteration material on Mars.
Thank you. Hi, everyone, and happy Pi Day. I'm Jade Camellis. I'm a PhD candidate at the University of Hawaii. And today I'll be telling you about my study of the iron serpentine hysindrite using Visayar and Raman. So to get started, serpentine is a hydrothermal alteration product of ultramafic materials, and it has been detected previously on Mars using CRISM data. However, it has been hypothesized that it's possible that the amount of serpentine has been underestimated on the Martian surface. And this is because of the similarity between the spectral signature of non-trinite, an iron-rich smectite, and hysindrite, the iron-rich serpentine. And so they both have this band at 2.28. And so where we have detected non-trinite, it may have actually, some of it may have been hysindrite. And it makes sense we may see some iron-rich serpentine on the surface of Mars because of the iron-rich olivine that is abundant on Mars. So this motivates my work because it's very important to distinguish iron and magnesium-rich serpentine so that we can see if we are actually missing the signatures of iron serpentine. So hysindrite is unique in composition and structure to other serpentines. So it forms a solid solution with magnesium-rich serpentine lizardite and also the iron 2+ serpentine greenolite. And it's a poorly crystalline mineral, so it's slightly amorphous. But the most important thing is that in the serpentinization process, it produces 5 times more hydrogen than the magnesium-rich serpentines. And hydrogen has some important implications for habitability on Mars, mainly to do with the possibility that it's a key energy source for microbial life. And also it could contribute to the warming of early Mars. So interestingly, we've only detected magnesium-rich serpentine in Jezero crater with supercams so far. And so you can see there are 3 places, the delta front, the upper fan, and the crater rim more recently, where we have detected magnesium-rich serpentine. And these detections have been done through SuperCam's Visayar capabilities. And so here on the right, I have a few different standards. On the top is hysindrite. You can see the band at 2.28. And here we have the 3 magnesium-rich serpentine polymorphs, and they have bands at 2.33. And we also have non-trinite just to show the comparison. But here at the bottom is the supercam target, actually called Serpentine Lake, which was pretty cool. And you can see it has a band at 2.33. So it matches much more closely with the magnesium-rich serpentine. So just to reiterate, we have this hypothesis that we should be seeing more iron-rich serpentine on the surface of Mars due to the iron-rich composition of the olivine. But we have a paradox because we're mainly seeing magnesium-rich serpentine. So it begs the question, why are we seeing the magnesium-rich serpentine? Is this something specific with Jezero crater, or is this widespread? So I'm going to be thinking about those things. And in order to do that, I've been studying some terrestrial samples from the Duluth complex. These samples are thought to be Martian analogs compositionally, and the iron and magnesium concentrations are consistent with those of Martian meteorites. So I've taken these samples and analyzed them using supercam techniques, Visayar and Raman. So to start with the Visayar results, I've realized in these early stages of research that these samples are actually very heterogeneous. So in my results, I had seen different signatures of different minerals, including magnesium-rich serpentine, olivine, and I see the OH bands at 1.4 and the H2O at 1.9. And bands at 2.33, which is the magnesium-rich serpentine, but actually no band right at 2.28. And so even though these are definitely hisindrite rich, they're a mixture of many different minerals. And so this is an example of a hisindrite rich sample. And this here from Millikan has a couple examples of even mixtures. And I think that is what we're experiencing here is mixtures between the iron rich and the magnesium rich serpentines. So then we dove into the Raman, and I wasn't sure exactly what to look for in the data because it's very sparse, the information about the Raman signature of hisindrite. And I found a couple examples in the literature. There's one paper that just mentions it, and there's just very poor quality data in the RRUF database. And so we started looking, and I found many different minerals in these samples that tracked very well with the literature of the Duluth complex. So we found anorthite, lizardite, magnetite, pyroxene, graphite, and olivine, all very beautiful spectra, but nothing that looked like it could be hisindrite or had a band in the last slide. You can see it's about 590 where there's consistency. But we kept looking, and I started looking at the thin section specifically, and we saw these veins here. And when we pointed the laser at these veins, we saw a band at 585. It was very broad, which was interesting. And sometimes it had these peaks on the shoulder, which I realized to be anorthite, which is very common in these rocks. So we also saw hydration bands at around 3,600, which makes sense since serpentine is a hydrated mineral. And I just wanted to make sure that these were indeed Raman peaks and not fluorescence because of the broad nature of the peaks. And so I did this analysis using the 514 nanometer excitation wavelength and also 532. And we saw that these peaks were still there with both wavelengths. So that was a very good sign. We did notice, however, there is a slight variation in the peak center. And we believe that this actually has to do with contribution from other minerals that would be either mixed in with the hisindrite or very close. As you saw, it was very common to have this peak from the anorthite. But we did see that the hydration band was relatively stable at 3,600. So to conclude, we have not seen any iron-rich serpentine hisindrite in Jezero crater with SuperCam. However, we have been able to at least now know what to expect, especially in the Raman, if we were to come across any hisindrite. The VisIR results were actually also quite interesting because we have these rocks that we know have hisindrite in them. However, we weren't able to see the signal in the VisIR because of all the different minerals with the hisindrite, which is a very natural thing to have, of course. You usually won't just have a giant chunk of hisindrite sitting there. And so this tells us that it's very important we have these samples back home on Earth to do these laboratory studies. So it's yet another example of why that is so important, to know what's in these rocks, and we can look at them at very fine scales. So that's pretty much everything I have for you. I'm starting to look for postdocs, just by the way. So thank you very much.
Well, thank you to all four of our speakers. And if you could make your way up to the stage for our Q&A, that would be awesome. And while you're doing so, just a reminder to the audience, if you have questions for any of these speakers, If you could walk up to the microphone and state your name and affiliation and ask your questions in a civil manner. And if you are online, please type your questions into the Q&A and the moderator will read them. Okay, go ahead.
Jeff Berger, I mentioned at Johnson Space Center. I have a question for the first talk. I don't know how to ask this, but do you have a sense of, can you unravel the difference between like the bulk thermal niche of the rock and what is the fracturing of the rock? Because some of the units are more fractured than others.
Yes, that's a great question. It's hard because we're kind of having to, even though we're able to separate the sediment and rock components with our modeling, we can't necessarily separate the more than that spatially in the rock. So what we're getting is kind of just the total rock and fracture component. And because we're sampling these temperatures over the entire GTS footprint. And I mean, maybe there is a way we could do that in the future that would just add a layer of complexity to an already very complex problem we're solving. But I agree that that's an important distinction.
Yeah, and I follow up to that really quick. Like, do you think, because some of the units, the like millimeter scale to centimeter scale fractures are filled with gypsum, but some of them are filled with material that's the same composition as a bulk rock. So it's probably like a silicate mud, and they're pretty distinct different units. And I was wondering if that might be detectable.
Yeah, the fracture fill is tough too, because the fractures kind of increase that or decrease that bulk density of the rock. But then when you fill it in with similar materials, it may be hard to detect the difference. I mean, if you're filled with the silicate mud, then you would think that it would kind of lower the overall thermal signature of the rock, just because that mud is going to have lower thermal inertia probably than if there wasn't a fracture and a fill there in that rock. But yeah, it's difficult.
Yeah. Okay. Thanks.
Hi, Laura Breitenfeld from PSI. I have a question for Ashley. I was wondering if you could expand a little bit more about how your data doesn't overlap the other measurements of the G-band, and maybe talk a little bit about which compositions might be closest on that plot, or processes like temperature that might be influencing the G-band.
Just to clarify the first part of your question, were you asking regarding the graphite versus the rest?
I guess that plot with the graphite compared to your analog materials.
Yeah, so we have pretty large error bars, and some of that's because, Sherlock data is just noisier than data you collect in a lab. And for all of them, they overlap at least one meteorite and one terrestrial sample. So it's hard to kind of parse out what the origin could be or what the alteration history could be. But some interesting things we noticed was for the carbonate related G-bands in Apollo Temple, it plots near the carbonate in ALH. So that's interesting, but then we also see the carbonate G-bands and Walhalla glades plotting near a chert microbial And because the error bars, they're closest to those points when you look at the entire graph, but because the error bars are so large, it's really hard to convince myself and anyone else that that means, this one's a potential biosignature and that one's an aqueous alterated from carbonate, So we really can't say anything about the temperature or, the origin yet, because this is just going off of the Raman, and we need to bring that sample back and analyze it in the lab with other instruments. But the graphite is simply, it was off into the corner, and that's why we boxed it out. And none of the error bars, even as large as they are on some of our samples, they don't overlap in that region. So that's why we say it's not consistent with graphite.
Great. Thank you so much.
Stephen Jarrett, City University of New York. Also, question about the Raman carbon. It looked like in some of the plots there were some peaks, silicate peaks at lower Raman shift. I know Raman in mixtures is dicey, but I was wondering, are you able to say anything about the mineral assemblage or what the carbon is associated with?
For the silicate, it's based off of our reference samples. It's closest to plagioclase, and it appears to be most consistent with labradorite. But for the carbonate, it's harder to tell because the lattice modes that are sensitive to cations, we can't see those. They're like 300 and below wave numbers, and we see 800 to 4,000. So it's harder to tell for that. In the sulfate, the hydrated matches are as consistent with basanite, but for the unhydrated that we see in Apollo Temple, we're not sure. But I think, and I'm going off of memory here, I think Supercam saw calcium sulfate.
Awesome. Thanks.
Hi, I'm Haru from JAXA, Haru Tabata from JAXA. I have a question to the second talk. Yeah, could you tell us a bit about some EGA result that you were not able to talk in your presentation?
Sorry, could you repeat that?
So could you tell us a bit more about some EGA result that you skipped in the talk?
Oh, yeah. So, and just for clarification, I'm not on the SAM EGA team, but yeah, so the SAM EGA data is really useful for us to characterize we use the H2O releases to help with the clay mineralogy and the SO2 releases to characterize the amorphous sulfate. So many of the samples up until the region where we began to lose the clays were dominated by amorphous iron sulfate. And then as we started to see the shift to more amorphous magnesium sulfate, we also began to see the H2O or the SO2 releases consistent with increasing amorphous magnesium sulfate. So yeah, it's actually really nice how well they correlate. I was really happy to see that. So
Thank you.
yeah, thank you.
Hi, Roberta Fleming from Western Ontario. I have a question for Sarah.
Oh,
So
hi.
in
Hey, Robbie.
ChemMin, in your X-ray diffraction patterns, you said that the range for the amorphous material was 25 to 40 degrees 2 theta. Did the position center change as a function of composition of the bulk?
It does. Yeah. So it's usually around 25 to 32 theta. So I might get this wrong, but so amorphous silicate dominated materials are generally slightly higher 2 theta and amorphous sulfates are slightly lower. And Steve Chipra is doing some models with full pat to see if we can try to pull those out directly from the XRD data. They come with really large errors, and that's actually why some of our errors are so large on our amorphous abundances. But yeah, there is a slight difference in the 2 theta peak between different compositions.
And what do you think it means?
Sorry?
Why do you think this? Why is it shifting?
I don't know. That's a good question.
Thanks.
Thank you.
Britton Wogston, University of Tennessee. I have a question for Jade, the last speaker. I was wondering if you have any plans to get a pure sample of Hissingerite and see what it looks like in Raman and then compare it to what you're seeing, because I think your work's really cool.
Yes, thank you very much. I do have a couple of collaborators who also have some Hissingerite, so they were also going to look at the Raman spectra to see if it's at all similar. And I may be receiving one more sample as well, that I think we found online, and it's uncertain if it is Hissingerite, but I could do some other tests to see if it's pure. But I believe it is quite rare to find a sample, especially on Earth, that is pure Hissingerite. It's very common that there's many other minerals mixed in, like the magnetite and the olivine, and even the magnesium-rich serpentine.
I guess sort of a follow-up question if there's time. So your primary scans for your thin sections, you were doing point scans, right?
With the Raman?
With the Raman, yeah.
Yeah, so I was just finding individual places and tried to have a variety of different minerals, or at least what looked to be different, to see if I could find the different components.
That makes sense. So it would be really cool to see what would come out if you used like a confocal mapping system.
Mm-hmm.
And then you might even be able to average the Hissingerite veins to get a better spectrum. And I think that would be cool.
Yeah, that's a really good idea. Thank you.
Thank you.
I have a question for Jade as well. So, Al Imran from JPL. So you mentioned detection of magnesium serpentine and caesar crater. Do you know how large this detection is? Like, well, like how large these deposits in Jezero crater? Any idea of?
Yeah, the deposits in the crater rim, I believe, were the largest outcrop that we have come across. There was also the Amalek outcrop, which was more so in the delta front area, but more recently in the crater rim. I don't know if we have been able to determine specifically how far that unit extends, because we've only been able to like drive to a couple parts of it. But I think it's quite large compared to like what we have seen before. So it's hard to say specifically the scale of it, I guess.
Actually, since you're talking already, I have one quick question. So, what could you speculate as to why it all seems to be the magnesium-rich serpentines that you're finding, and you're not getting those iron ones that you said you might be expecting?
Yeah, good question. I mean, one part of this is the composition of the olivine that we are seeing. I believe in this region is more magnesium rich, so that would make sense. So I think it just has to do with the composition of the material that was altered into serpentine, and that I think we are seeing forsterite 80, 89 or so with SuperCam more recently.
Matthew Huber, Planetary Science Institute. Question for the first speaker. You're estimating porosities up to 2/3. What does that look like?
Yeah. Those porosities seem high, and I realize that that is how that appears. So I mean, I can say this from the lab work that I did on these, Mars-like rocks. We saw our highest porosities in like pumice samples and very vesicular igneous samples, but we also saw some pretty high porosities in the, 50s, almost 60% in some of our mudstones that were just very, very, they were not very well cemented. And so, I mean, yeah, it's true. I mean, there are rocks that exist that way. Now, whether the rocks in Gale are really showing porosities that high, is debatable, but, and I agree. So thermal inertia is just a really complicated, multifaceted property that can be affected by so many different factors that, I would say take those values with caution, definitely.
If I can pull up. And so all of those porosity values are coming from the thermal data. So just looking at the pictures, you're not seeing the direct difference between a very high porosity and very low porosity mudstone.
Yeah, it's just from the thermal data. So okay. We recognize that's kind of limited. Yeah.
Hi, I'm Jung from Umeå University in Sweden. I have a question for James, the last speaker. So have you ever considered about the interference of carbon dioxide? And the second question is that, have you ever tried or think about to measure your mixture with other laser, like red laser in Raman, just to see if you get a better result?
Yeah, thanks for those questions. I'll start with your second one. I have measured these samples using a 785 nanometer laser and 830 as well. So I've used a few different instruments. I think this signal of Hisindrite is quite weak, and that's due to the nature of how it's slightly amorphous. And so with those higher wavelength excitation lasers, I was not able to actually see the signal. There was also fluorescence. So the fluorescence, I think, made it very difficult to see anything. And so that's also why I decided to try another green laser, like 514 and 532, because they will have a stronger signal than the red laser. And also it's similar enough that the spectral characteristics wouldn't change as much between them. And so I could really see if those peaks were consistent. And in terms of if I had thought of contributions from calcium dioxide, sorry, what was it?
Carbon dioxide.
Oh, carbon dioxide. I've not really considered that. Yeah, I'll think about it.
Because supercam is shoot quite far, right? And then carbon dioxide is quite much in the air in Martian atmosphere. So
Right.
maybe it's also very big interference for the data.
Right.
That's what I guess. And
Okay.
I feel you because I also work with Raman as well. It's really dusty and it's really fluorescence.
Oh, sorry, was that last part?
I mean, like the dusty sample, like the sample with a lot of dust like Mars, it gets really fluorescence in Raman. So I feel you.
Yeah, absolutely. I believe the carbon dioxide peaks are higher wave numbers. So unless I'm remembering incorrectly, I don't think those would contribute as much to the bands around 590.
Rob Platt, Imperial College. Question for Jade. You mentioned that it's very difficult in Vis-IR spectra to tell serpentine, Fe-rich serpentine apart from non-trinite, so Fe-rich clays. How do you tell those apart from Vis-IR spectra?
I haven't done work comparing the two in very much detail. I do know there are people who have done that work and have seen there are slight differences. Just from what I had gleaned, the non-trinite bands were there was a little bit of variation, but they were like more around 2.29, and they could be at 2.28. But it seemed from what I saw with Hissendrite, and it's also quite sparse Hissendrite in the Vis-IR databases, but it seemed pretty consistently at 2.28. So there's probably more details than even just that one band, but I think that is, if you see it at 2.29, 2.28, that would tell you something.
Okay, I have a question for Sarah. And this is actually more just because you ran out of time when at the very end of your talk. Could you give us a takeaway message? Just what would you like us to remember from your talk, and any points there that you didn't get a chance to cover?
Oh my gosh. I guess that the amorphous abundance and composition does appear to be changing as the marsh and environment became more dry. So we see a lot of these changes in mineralogy, and that is also, I think, reflected in the composition and abundance of the amorphous component. But we do have to take into account that we are still seeing alteration minerals, and the models that we, I guess, put forward in the paper need to also keep this in mind as well. So.
Thanks. No questions online today, so we have one more minute. If there's one person who wants to come up, or if anyone wants to give a closing statement. Oh.
Sure, I'll ask something. Phil McCausland, Western University. This is for Sarah. Howdy.
Hey, Phil.
Howdy. Very quickly, just notionally, is there a grain size change going up section in the rocks?
That's a really good question. I know that we moved from subaqueous primarily, like in Glentordan, we had a lot of mudstones, and a lot of the stuff that we're seeing right now is subaerial. So that would be a really good question for the sedimentologists on the team. I don't want to give you a number because it would probably be wrong, but I think we are primarily now in sandstones compared to mudstones where we were previously.
Just interestingly, there may be, because the lower part is water lane environment, there may be a different set of grain sizes, maybe larger. And then as we get up into more subaerial and dusty, there's just nothing to limit grain sizes, so they get really small, is one thing perhaps to look for.
Sorry, could you repeat the question?
Oh, it's not a question.
Oh,
It's
okay.
One thing that maybe to look for is grain sizes
Okay.
get really, really small
Oh,
as you go up
yes,
section.
I think we're out of time
Thank
for
you.
the discussion. Thank you very much. So moving on to our second block of 4 talks. Oh, yes.
So the first speaker for this block is Sarah Lam, and talking about machine learning strategies to distinguish iron sulfide oxide and oxyhydroxide mineral using Raman and Libbs spectroscopy.
All right. So I am Sarah Lam. I'm a PhD candidate from the University of Kansas. So the project motivation for this talk is that if we go to ocean worlds or even just on Mars, we are getting so much data back. And wouldn't it be great if we actually had a system in place where it could identify the minerals, at least with some confidence? So we start with iron minerals, both because of their abundance, but also because that they could be critical for origins of life and habitability. So they're great because they can facilitate thermodynamically unfavorable reactions. They can allow the concentration of organic compounds. So there's a lot of use to these iron minerals, and it'd be great if we could identify them with a lot of confidence. So the idea is to use both Raman and Libbs to see which method is easier to accurately identify these minerals with machine learning, and maybe also do data fusion. So the model overview is that we are going to take all of the data that we collect, and we are going to break it into a training data set for these models, and then a validation data set. So the second one is going to be essentially put into the models. The labels will be taken off, and the models will have to see if they can accurately identify them. So after we have the training data set, we actually take that really high dimensional spectra, and then we reduce it based on unsupervised learning models. So we've used PCA, principal component analysis, hierarchical clustering, and then k-means clustering. So we're taking 858 features from that spectra, and we are then putting it just down to 3 to 5 features based on how we're combining models. And the idea of this is we need something that is both robust, lower variance, but also we need this to be as time consuming or as least time consuming as possible, because there's just so much data that we're getting back from Mars and other planetary missions. And then once we have those new features, we then train them on supervised models, linear discriminant analysis, support vector machine, random forest, and then extreme gradient boost. So once we have that original model made, we take the validation set and then we do the same thing to it, where we take that 858 features and then we drop it to 3 to 5, and then we put it through those models and see if it's assigned correctly. So the first goal is to first kind of figure out those optimal parameters for the machine learning, which unsupervised learning technique's the best, which supervised learning technique is working the best, and then from there, determine how much data actually needs to be available for accuracy. So this is just a little bit of the Raman data we collected. We actually have 4,000 spectra over 12 different minerals, and each mineral we have multiple different actual samples from. That way we can cover variability of just natural mineral samples. We did this on a 785 Raman laser. That was to prevent as much oxidation as possible. And then we collected the Raman spectra from 170 to 1,200 Raman. So the first thing from there is once we take that spectra, we put it into that principal component analysis. So on the bottom X, we have PCA1, and then here we have PC2. Here is PC3 against PC1, and then PC2 versus PC3. And you can see that in PC1 and PC2, we have a few different groups. So this is galena. It plots pretty far away from each other. Here's magnetite. And then here is both hydronium jarosite and jarosite. So while PCA is not doing a good job separating the two from each other, it does recognize that these are part of a family and should be separated out from everything else. And then when you do PC1 versus PC3, magnetite is still by itself, galena is by itself, but those jarosites now are getting very close to this overall group. But our goethite is starting to come out by itself. And then PC2 to PC3, goethite and some of pyrrhotite's coming out. The jarosites are back separated from the rest of the cluster, and magnetite is still very far apart. So K-means is a similar technique to PCA, except it then groups them. So magnetite's grouped together, galena's grouped together, hydronium jarosite, and a single pyrrhotite spectra was together. And then the other two, it kind of struggled with. And then the last one was hierarchical clustering. So it puts them in order from left to right, or what it thinks is the most separate. Once again, galena is by itself. The jarosites are intermixed, but they are plotting together. Magnetite, chalcopyrite, and then some of the other ones kind of all got grouped together because it wasn't really sure. So once we have all that spectra and we've now put it through that unsupervised learning and we've reduced the dimensionality, we then run it through both LDA, SVM, XGB, and RF, random forest. So this is just one confusion matrix that we are getting out from it. So this is when we use all three combined inputs. So we're using what we've got from PCA, high clustering, and K-means. And you can see, for the most part, the only ones that were mislabeled are the ones in red. So overall, you can see, so our unsupervised learning inputs are here, and then these are our supervised learning. So XGB and random forest did the best. LDA never really did well, and SVM kind of had some hit and miss. So then we wanted to see how sensitive the model was to data availability. Because again, the whole idea is to make this as fast as possible. But do you need to put in 3,000 spectra to get accuracy or not? So I then changed the percentage of how much training model we're sticking in. So 5% is going to represent 200 spectra, while 90% is representing about 3,600 spectra. And then we realized that PCA was doing the best, so we took out some of the other models just for simplicity, honestly. So you can see right off the back, LDA not doing great, SVM better, but XGB and random forest was doing the best accuracy-wise. So about around 30 is when it plateaus. So here is that same data of just extreme gradient boosting and random forest as a line plot. So the known amount is also like the training set. So about around 30% of the spectra, which is about 1,200 for us, it kind of starts to plateau off. I mean, there's still some variability, but it's showing that you do not need to put in all the spectra you've ever collected to get accurate results. So the RF, which is our solid lines, did slightly better than extreme gradient boosting, and both of them alone outperformed LDA and SVM. And the combined inputs, so all three inputs together, consistently performed the best, which kind of makes sense. So this is a table of the accuracy based on the mineral itself. So as I showed you earlier in some of the unsupervised learning, there were some minerals that really were able to separate out from the other ones. So chalcopyrite, galena, magnetite, and even sphalerite did very well. Goethite did better at XGB than random forest. But what's most interesting is pyrrhotite. And it did never did well in XGB, except maybe once. But random forest was able to get it 100% of the time. So pyrrhotite is the one we actually have the least amount of spectra on because it was constantly oxidizing with the laser. We have only about 13 different spectra over it. But Random Forest was able to figure out that pyrrhotite was pyrrhotite. So pyrrhotite oxidized rapidly under the Raman laser, but with Random Forest, it worked very well. Combining the inputs improved the model. Random Forest or extreme gradient boosting both did very well, though Random Forest looks like it was just a bit better, especially when it comes to sparse data. And we only needed about 30% of the spectra in the end. And infusing libs should improve accuracy overall. Oh.
Thank you. Our next speaker is Rob Platt, talking about rapid mineralogical mapping of oxyaplanum using machine learning with CRISM data.
Yeah, good morning, everyone. Thank you for sticking around till Friday morning. My name's Rob Platt, and I'm here to talk about our approach to rapid mineralogical mapping of oxyaplanum using machine learning with CRISM data. So I'm going to talk to you quickly about oxyaplanum, which is the landing site for the ExoMars Rosalind Franklin rover mission. Then introduce CAMEL, or the CRISM analysis with machine learning software we've developed, and show an application of it to the clay stratigraphy in oxyaplanum. This is oxyaplanum then. It's a 200-kilometer square low-lying area between Chryse, Polynesia and Arabia Terra, right on the crustal dichotomy of Mars. It was initially sort of scouted out as a target of interest because of the sinuous fluvial channels that are morphologically evident and the sediment fan deposit, which both are pretty good indications that there was a significant amount of water rock activity there in the geological past. There's quite a lot of CRISM data over the area, which gives us some idea of the mineralogy of the surface. CRISM data gives us pretty detailed at 18 meters a pixel spectroscopy data of the surface in visible through to shortwave infrared. We can extract spectra from each pixel and identify key absorption features to figure out what the mineralogy of the surface is. The problem with this is that it's incredibly time consuming to go pixel by pixel through an image, and there's quite a high degree of expertise required. So the barrier to entry for using CRISM data is quite high, and this kind of has made it very underutilized. Our approach then was to develop a machine learning model to potentially lower the barrier to entry for this data and try and speed up the process of analysis. We used a variational autoencoder model, which is a form of generative machine learning architecture. So it's made of two neural networks, an encoder and a decoder. The encoder takes in some input spectra and compresses it to a learned latent representation, which is lower dimensional. And then the decoder takes the latent and attempts to reconstruct the original input. There's no actual classification element to this, so we have to make it slightly more complicated. So we actually use two encoders. Both produce their own latent spaces, which are then used by the decoder for the reconstruction. But off this second latent space, we have a classification neural network, and that's what's producing our mineral class predictions. We then wrapped this model into a software package called CAMEL, or the CRISM analysis with machine learning. This is a free open source software package that's available to anyone that lets you load in CRISM data and visualize the imagery and the spectra, calculate summary parameters to highlight mineralogy of interest, and then run machine learning to predict the mineralogy on a pixel by pixel basis. It's a no-code platform, so you can literally just double-click run it, and it's platform and operating system agnostic. So we hope it's available for pretty much any planetary scientist that has ever wondered about using CRISM data or thought it would be interesting to go away and try this and use it. If you want some more details on CAMEL and on the actual methodology behind it, feel free to scan the QR code, which will link you to a Mars 10 abstract and the actual code base for CAMEL. What we did with it is we took all of the CRISM imagery of oxyoplanum and ran it through this software, which took all of about 20 minutes, which then gives you a mineral map over the entirety of oxyoplanum. We filtered the results so that we are only actually displaying anything that the model was at least 75% confident in and had a minimum connected component of at least 10 pixels. There were at least 18 different mineralogies identified in this map, but the 4 sort of most dominant and most broad areas were iron-rich smectites or nontronites, clay carbonate mixtures, magnesium-rich smectites or saponite equivalent, and pyroxenes. If we zoom in to the eastern edge of the area, we can compare the results that were produced by Camel to those that have been previously reported in the literature. And we can see that the area of magnesium-rich smectite identified in the literature agrees really well with what Camel identified. Except for we have this additional area of magnesium-rich smectite that was missed previously. If we compare that new area with the type spectra for saponite and overlay the key absorption features, we can see they pretty broadly agree. So we can be quite confident in the results that are given to us by this machine learning model. If we go across to the center of the landing site, we can once again compare to the previous established literature. And again, we're identifying more areas of clays than previously seen. So it's suggesting that these clay deposits that we see in oxyoplanum are actually far more widespread than we previously thought, at least in terms of the CRISM data. And once again, we can compare the newly identified area to that identified previously and see that it does once again match really well. So we have quite high confidence in this result. So as well as the 4 peaks that are identifying this as a magnesium-rich smectite, there's also this quite broad peak at 2.5 microns. This has been identified previously and was thought to be prevalent all across oxyoplanum in the clay stratigraphy and has been thought either to be mixing with either a second phyllosilicate phase or a carbonate. But if we zoom in even further, Camel identified this area of iron-rich clays. And if we compare the iron-rich identified clays to the surrounding magnesium spectra, we can see there is a slight shift in the peaks at 1.4 microns to longer wavelengths and at 2.3 to shorter wavelengths that support a slight iron enrichment in these spectra. But the key bit is we no longer have this 2.5 micron feature. So that suggests that these iron-rich clays that the models picked up are actually probably quite a lot purer clays than identified in the magnesium clays around it. If we look at slightly longer wavelengths, there's nothing really to differentiate them. So as to whether it's a second phyllosilicate phase that it's mixing with or a carbonate, we can't really give any information on that. If we compare this to the morphostratigraphic map that was released last year as a high detail high-rise map of the landing site, we can see that the iron-rich smectite agrees really well with the second lower bedrock unit, and the magnesium-rich smectite agrees really well with the third lower bedrock unit. If we then look at the strat column for this, what we're suggesting then is that we have a magnesium-rich clay in this third lower bedrock unit that's mixed with this secondary phyllosilicate or carbonate. And as we're transitioning through the mid-Noachian into this second lower bedrock unit, we are iron enriching these clays, and it's a much purer clay stratigraphy. To conclude then, we've completed some rapid geochemical mapping over oxyoplanum using Camel. We've positively identified this wide extent of phyllosilicate mineralogy, much more than has been previously identified. We've observed these possible lithological changes in the mid-Noachian sediment that we are hypothesizing currently are either a change in depositional environment or more likely a change in the groundwater chemistry through the Noachian in the area. That's all from me. Thank you very much.
So our next speaker is Anna Lomishvili, and the title is Machine Learning Aided Light Tune Vein Identification in ChemChem RMI Image Data.
Hello, so I'm Anna. I'm a final year PhD student at German Aerospace Center, and here are my co-authors. Before jumping into the studies that I'm going to present, I want to quickly review the ChemChem instrument that is mounted on Curiosity rover, and it consists of two parts. First is the LIBS, laser-induced breakdown spectrometer, which shoots the laser to the target, creates light-emitting plasma, and then this plasma is collected by spectrometers. And from the spectra, we can derive chemical composition of the target. We can see the very first spectra acquired by ChemChem. And the second part of the instrument is remote microimager, and it takes context images. We can see also the corresponding context image of this very first spectrum. These context images are taken before and after LIBS measurement. And then we can create also such kind of mosaics. My study is mostly focused on working on these RMIs. So my previous study was more about going through the targets over the traverse and trying to implement a machine learning model which would classify these targets into specific textures. So first I derived these 9 different classes, and then I implemented a machine learning model that would distribute these targets into these classes. And here we can see also some examples of those targets and corresponding classes. And if you're interested in this work, you can, of course, check this QR code and see my LPSC abstract for that. So we wanted to go a step further, and we wanted to find if there is some kind of correlation between the texture of the target and the LIBS spectrum. And for that, just the first work was not enough, and we wanted to have more like pixel-wise knowledge of what kind of texture it is. And for that, there is this field in machine learning called semantic segmentation, and it takes care of this pixel-wise classification. We wanted to start with the class that was more or less known that there is a correlation between this spectra and texture, and such class was this light tone veins. And we know that these light tone veins tend to have correlation between high calcium levels. And we wanted to do this semantic segmentation of these light tone veins. For that, to train a machine learning model, we need input, and we need also a ground truth labels. We already had inputs as RMIs, which were with light tone veins. And for ground truth labels, we had to label every pixel. And for that, we labeled the pixels that were not consisting the light tone vein with black pixels and with white pixels if there was a vein. And because this labeling is quite laborious, we only labeled 55 images. So here is the example of this ground truth mask. Then we had to fit this into semantic segmentation model, and one of the popular models is called UNet. I won't go into details how this model works, but the idea is that it's fully convolutional neural network. And I implemented this with different settings. And this is one of the results. So we have this input, we have these ground truth labels, and we have also the prediction. And we can see that this prediction is more or less more sensitive than our ground truth labels, and it also detects these very thin light tone veins. But we should also know that when we create these labels, there's also a challenge to detect and to check if there is this thin fractures are really filled with calcium sulfate. So there are some inaccuracies when it comes also with manual labeling. And we wanted to address also this manual labeling. And for that, we use this LIBS spectrum, and we created LIBS generated images. we labeled with black pixels if lip spectra showed that there was no high calcium levels, and with white if there was high calcium level. And with gray pixels, we labeled the areas where there was no lips measurements done. So it was we didn't have any information about the chemical composition in those areas. So the one way is to have these separate inputs in this unit model, and another way is to combine these two types of data is to add the lip generated image as an additional channel. So if we have an RGB channels in the image, we can add this lip generated image at the fourth channel. Now, how to check if this model is performing well or not? For that, we need performance metrics, and one of the commonly used performance metrics in semantic segmentation is mean IOU, and it is basically the ratio of the overlap between these masks, so the one that we labeled manually and the prediction, and it is divided by the union of those two images. Another metric is F1 score, and it most like tells you the ratio of true positives and true negatives. And here we have this table that shows also different settings that I implemented. I won't go into details. We can always talk about it later. But the rule of thumb is that if a semantic segmentation model performs with mean IO of more than 70, it means that it already does a decent job, and we can use this data in applications. So for that, here we have an example of an application. So in the first plot here, this is the calcium oxide abundance over the traverse. And there was also a nice talk on this on Wednesday by Matt, and he was using shot by shot data. But now back to my plot. So it just shows the density of calcium oxide over the traverse. The next plot shows I used my previous model that can tell if there is a light tone wane of the target or not. And for that, I plotted it with some along the traverse where this method detected that there is a light tone wane target. And then I use this data for my new model that tells where those light tone wanes are. And for that, I had these white and black pixels, and I could also calculate this density of wanes for each target. And here, that's the last plot. That's the last plot. And we can see that these three plots do not really align with each other. And this happens because there are a few reasons. So there might be high calcium levels in the lip spectra, but on the target, there might not be a light tone wane. Another reason is that there might be a light tone wane detected on the target on the RMI, but the lip shot might not hit this target. So here we have one of the examples. So we have this light tone wane here, but the lip shot did not really hit the wane. So because of that, these two models tell us that there is a high density with the wane, but low, but the lips shows us that there is no wane. Now to circle back to the papers that worked on this topic. So we have these two papers here that explored these light tone wanes over these 13 regions. And the take-home message of this presentation is that this model allows us to detect these light tone wanes pixel-wise and be more efficient and quickly to process all this data along the traverse. Now I'll quickly just summarize. So I have implemented the semantic segmentation model for these light tone wanes with different settings. And we should also know that this can be more like a stepping stone. So we can also implement the semantic segmentation for different classes. So we can also use it to determine where there is a soil and where there's a bedrock, if the lips really hit this soil or not. So we can also extend this model to different classes. But one thing is still obvious, that there is still challenges to have these labels, because we already saw that it's difficult to already see where we have these light tone wanes, and it's also a challenge to have consistent labels. So today, this is for all. If you have questions, I'm really happy to answer during the discussion. Thank you.
All right, so the last speaker of this segment is Lars Alt and talking about automating region of interest ROI selection for spectral analysis of Mastcam Z observation.
All right, thank you. Yeah, so today my name is Lars. I will be presenting some ongoing research with the Western Mars Lab, led by Dr. Melissa Rice, in collaboration with Mastcam Z aboard Perseverance. So I just want to start by giving kind of a high-level overview of Mastcam Z for those who are less familiar. It's a set of two multispectral cameras that are mounted up here on the mast of Perseverance. And in particular, it has 11 narrowband filters as well as 3 broadband. And together, we're able to approximate a spectra at each pixel value in the image that the cameras capture. And so what we're really, the kind of guiding motivation for this work is that extracting spectra from Mastcam Z observations is currently a very manual and time-consuming process. And so we hope to speed that up using some machine learning concepts. And yeah, I just want to kind of give some kind of intuition for what that process currently looks like for the human evaluators. And it begins with kind of an interpretation of various spectral products, so enhanced color stretches and decorrelation stretches of the scene. And from that, the humans identify spectral regions within the scene that are relevant and capture the geologic context, as well as the spectral diversity. And this process currently takes around 40 minutes. And so this is kind of a very laborious and time-consuming process, and that's kind of the guiding motivation. And so with the algorithm, we hope to speed up this process, as well as reducing inconsistencies in the ROI that are labeled, and reducing sources of error. And so just broadly, to recap, the goal here is to develop an algorithm to automatically select ROI within the image to capture geologic and spectral diversity. The geologic is the key one here. We're not just interested in spectral end members. We also want to capture that. And to kind of illustrate how the algorithm is working, I want to focus on this sample scene from Mount Washburn. We chose this one just because of its compositional diversity. You can see the light tone float rock, kind of a cool scene. And just, again, guiding motivation, these are the ROI that the SPDLs, the science payload and downlink leads, who are the human evaluators, have classified for this particular scene. So this is what we hope to see as the output of the algorithm. So the algorithm itself has 3 overarching steps, namely pre-processing, interpreting the physical context of the scene, and then finally selecting ROI. So I'll go through those here. We begin by pre-processing. This is pretty straightforward. We're just using the same kind of architecture that the rest of the Mastcam Z tools use. So we map the left and the right pixels together, and we're just using a homography matrix, so describing an isomorphism between the 2 viewing angles. We then do shadow and sky masking across the image so that we're only prioritizing spectrally relevant locations within the scene. And then finally, a normalization step, which is kind of standard for machine learning. We next use the segment anything model from Meta to segment the image. And the kind of intuition behind this is that we want to capture the geologic context. And so this step allows us to create masks. So if you look over here on the right, all of these kind of specks, in this case, float rocks, are representing individual mask. And so this is to ensure that we're capturing ROI on all of the relevant geologic features within the scene. And now for kind of the last major step in the algorithm, this is the spectral analysis portion. And for this, This step is actually applied to all of the masks from the previous step. And kind of to illustrate it, I'll just be focusing on that light tone float rock from before. So this step, we're using kind of a custom recursive implementation of the k-means algorithm. And we use variance in the classifications as kind of a base case or a stopping parameter. So we basically cluster up until we hit that prescribed threshold, and then we backstep to the previous set of classifications, and those are the ones that we take. And this is kind of to represent all of the key spectral characteristics within the masks. And again, I just want to highlight that this is applied to all of the masks from the previous step. Next, for each of the masks that are identified in that last step, we compute a density map and find the highest density region, and that's kind of the region that we target for the ROI. And we build the ROI around that. And what we're left with are ROIs for all of the major geologic regions that represent the spectral kind of characteristics thereof. And as you might imagine, this leads to a whole bunch of geologically relevant spectra, but just a ton of them. And so now the goal is to minimize that set down to only the representative spectra, or ROI in this case. And so to do that, we have kind of two major steps that we've implemented. The first being clustering these ROI based on their spectral characteristics. And this is a pretty straightforward process, but the second step is actually kind of cherry picking the best ROI from all of those classifications that's the most representative. And this is where this kind of how do I go back? Okay, this is kind of where this heuristic function here comes into play. And we're basically trying to maximize the pixel count. And so that's what this is, kind of the normalized pixel count, and we're subtracting from it the normalized variance. Apologies, that says error. For the ROIs. And this is kind of builds in some of the intuition that the SPDLs, the human analysts, use when selecting ROI for a particular scene. And what we're left with is this minimized set of regions of interest within the scene that are able to capture kind of the geologic as well as the spectral diversity. And if we compare this to the SPDL classifications, you can see that importantly, the spectral characteristics are being captured. So the ROIs aren't necessarily on the same geologic features, but they capture the same spectral properties. And because of that, we can kind of extrapolate that they're representative of the same type of mineralogies. And so now I just want to give some pretty pictures, a few example scenes of the algorithm. And I'll begin here with Whale Mountain, just kind of a deposition scene, pretty straightforward. We also ran it on a few abrasion targets. This is Dorb's abrasion. You can see in this particular case, it hasn't actually selected any ROI in the center of the abrasion, which we would have liked. But this is something that the algorithm can kind of be fine-tuned for. There are kind of hyperparameters, and we kind of ran the vanilla version of the algorithm across these samples just to kind of get a broad understanding of how it's classifying in general. Here's Whaleback Ridge. You can see kind of this rock with a whole bunch of different faces. Hollowell Park. And for this scene, we kind of wanted to test the fore, mid, and background capabilities. We want to make sure that we're capturing ROI across the full focal range. And finally, Lobster Cove. And yeah, kind of some interesting float rocks. And yeah, so for conclusions, as I mentioned initially, the algorithm is still a work in progress. And so we're continuing development with the MassChem-Z team in correspondence with the SPDLs to kind of build in further intuitions into how we're selecting ROI. And yeah, we have many improvements planned for the future. yeah, since kind of the last update, we've implemented the segment anything model, and the ROIs, as you've been able to see, hopefully, are able to capture kind of the spectral and geologic variability within a scene. In terms of next steps, we plan on incorporating the algorithm into a command line tool for use by the SPDLs and eventually a GUI. And we also plan a quantitative test across all of the spectral classifications that the ROIs have captured. So yeah, I'll leave this up. Thank you, everybody.
Yeah, thank you to our four speakers. And it's time for the Q&A now. So if you can mosey on up to the front and get situated, and we can, and those in the audience, if you have questions, if you can also come up to the microphones. And nothing on the, we have 29 people in the online one, and no one's asked a question yet. So hopefully someone can speak up from the online community here as well.
Hi, Ari Essenfeld from Los Alamos National Lab. Thanks all of you for such interesting talks. Exciting to see all the different machine learning models in use. My question is for Anna. I'm wondering, you may have mentioned this, and I may have missed it, but have you thought about extending this approach to other textural features, such as maybe nodules or other diagenetic features?
Yeah, I guess that was also the motivation of the study, to do it for the rest of the texture classes that I determined in my previous study. But as I mentioned, it's really challenging and it's time consuming to do this manual labeling, and more like foundation models such as SAM does work in our case. It doesn't do that well. So one needs to really take time and do this manual labeling. And because it's the end of my PhD, I don't really have that much of time to extend it, but you're welcome to continue the work.
Thanks so much.
Britton Roxlin, University of Tennessee. I have a question for Rob. I thought that it was a really awesome example of how your camel model can work, looking at a previously mapped and well understood area. You mentioned that you used a 75% confidence level when you were pulling spectra from camel. And I was wondering what sort of level and process you would suggest for the layperson like me with Chrism using the camel software in a new area that hasn't been previously studied when it comes to trying to understand the mineralogy.
I've found the combination of 75% minimum confidence and then a connected component minimum of about 10 to work pretty well. I think you can somewhat scale it to your own confidence in your own abilities in identifying Chrism spectra. So the more confident you are, perhaps you can reduce that. And if you've never used Chrism before, then put it at 90%, and then you really are confident in the model results. That's entirely tunable for you.
Okay, awesome. Thank you.
Hello, this is Michael Phillips from the University of Arizona. Question also for Rob. Great talk, and I'm interested to follow it up with you more on that. But I wanted to see if you could say more detail about the two different encoders you were using. It wasn't entirely clear to me what each was doing. So it looked like you were getting a reconstructed denoise spectrum from one, but it wasn't clear to me how that fed into your classification of the latent space vector from the other encoder. So yeah, how do they relate to each other, and why were there two?
So both encoders and then both latent spaces are used by the decoder for the reconstruction. We only use one latent space for the classification. So the idea is you separate the useful information you need for classification from all of the rest of the latent information you need to make the reconstruction. So your background signal, your continuum that you need for the reconstruction should in theory be separated into the first latent space, while the key absorption features and everything else that the model decides is useful for classification goes into the other latent space. So you effectively make your classification task easier for your classifier by splitting your latents.
Yeah, and so the way you're kind of ensuring that that happens is that is there any communication with those two during training, or yeah?
Yeah, so the classifier and the VAE are trained simultaneously. You train them end to end.
Okay.
We have a online question from Alice Goulart from Los Alamos National Laboratory, and it is I'm wondering, does the decrease in training size work for complex or unseen samples, or is it just for a pure set of select material? Have you tried the decreased training size on a more complex test set? Unfortunately, this question was not specifically directed to anyone, so I'm not sure who can answer it much
I'm guessing that was
better.
me since I was playing with different sizes of training set. So at the moment, sir, can you reread it? It was about like the purity of minerals.
Does a decrease in training size work for complex or unseen samples, or is it just for a pure set of select materials?
So right now we were only using kind of like pure minerals. In future work, we want to start like mixing them and seeing what happens. But at the moment, we only had 12 minerals, 4,000 spectra. But we had quite a few mineral or samples per mineral to account for variability. So I also have, I think the word pure is also interesting for pyrrhotite since it is it has a changing chemical formula. It's FeX to sulfur 1 minus X. So I wouldn't necessarily like the word pure because it did have a changing Raman spectra that we could see. But as my slide showed, random forest could still figure out what pyrrhotite was.
So connecting to that question from the same, but no other phases than the intended.
Sorry, repeat that.
It's a follow-up question by the same person. So, but no other phases than the intended.
No, we didn't have it set up for like that.
Let's take a question in the room.
Hi, question for Robert. So I'm Miriam from the physics lab of UBurn. I did a lot of spectral clustering with Prism myself, so I would like to know if that's possible to extract the classes as a binary mask from the GUI you did for GAML.
Yeah, the way the GUI is set up is you can export the Prism image with the pixel classification and the confidence scores sort of appended to the end of the spectral bands. Load that into MV and then do whatever you want with it in MV. We basically just then map projected it and stuck it straight into ArcGIS to do the analysis.
Cool. So I use Python rather than MV, but we'll try. Thank you.
It works in Python as well.
Okay, so we have an online question for the last speaker by Walter. Any plan to use the MCAM-Z ROI algorithm directly to the rover? Note CCAM / SCAM have already their AEGIS algorithm on board.
Yeah, so we don't plan to deploy it on board. It's going to be a pre-processing step for once the data have been downlinked. So yeah.
Go for the next.
Britton Lawson, University of Tennessee. I have another question, but this time for Anne. So you're doing pixel per pixel classifications, and I understood the manual mapping or classifying for the veins, but then you were mentioning that you wanted to apply it to other textures that aren't as black and white. And I was wondering how that works when the texture, you need multiple pixels to identify it, say with the soils versus bedrock, but you're doing a pixel by pixel classification. I was wondering if you could elaborate on that.
Yeah, sure. So the semantic segmentation works in a way that it's not just extracts the just single pixel, but it also like tries to learn whether it's part of some object. So that's, for instance, if there will be this patch of soil, it will learn the whole patch of soil, but also it tells like, is this pixel the neighboring, the same class as a neighboring pixel? So it, because also it uses convolutional neural networks and it also has this moving window, it also checks the neighboring pixels. So it won't be just a single pixel, but it will be more like a spatial knowledge also.
Thank you.
I also have a question. Lindsay McHenry, UW Milwaukee. I also have a question for the third speaker, Anna. And I was wondering if you just have a general feel for when you're applying this technique to the veins, were you finding, was it picking out on signals that you weren't seeing with your eyes that were actually valid? Could this give you an improvement over interpreting manually other than just time?
Yeah, so for that, I think lip spectra helped me. So sometimes I could not really see it visually really well, and I could not like distinguish whether it's for the part of the vein or the bedrock. And then if there was a shot of lip spectra and it told me that there's a high calcium oxide, then I would be more confident.
Thanks.
Al Imran from JPL. I have a quick question to Sarah. So I see you use PCA, and I only see two PC axes. How much variation those two PC axes can explain for the original data, and how did you decide the PC axis? Like how many PC axes should be in your algorithm?
So we decided on 3 based on a scree plot. So that was the elbow method of what it was explaining before it kind of fully just kind of plateaued there. So we decided 3 was the best. For the first one, if I remember correctly, I think it was about 40% explained for PC1. And then I think PC2 was about 17%, and then PC3 was about 9%.
I have a question for the last speaker. Sorry, I missed your name. But it sounds like your automated ROI identification is useful on like a tactical or maybe short-term strategic time frame for like short turnaround in doing this. But I'm curious if you think it has a lot of value for looking at all the previous Mastcam Z images, and is it also something that would be easily transferable to Mastcam on Curiosity?
Yeah, no, thank you. We plan actually on like rolling it out on like the historic Mastcam Z data set, on the full data set, and that's kind of what I was getting at the end with the we want to do like a full extensive comparison between the SPDLs and the algorithm classified ROI. So that's something we plan to do, and we hope to use whatever results we get from that to fine tune the algorithm so that it's able to generalize really well. And so that we can kind of implement it as an automated step in the pre-processing. Yeah.
And then is it easily applicable to Mastcam on Curiosity as well?
We haven't tried it on Mastcam yet. We have tried one PanCam scene, but yeah, we're getting to that.
Okay, great.
Yeah.
Thanks.
Hi, Lindsay McHenry, UW Milwaukee again. And I have a question for Sarah Lamb. And my question is just, why did you choose to start with this, with the sulfides, oxides, and oxyhydroxides? Why, what, is there some reason you selected that group of minerals to start this process?
Yeah, so the idea behind the iron minerals was one, the
availability they are on Mars, and then two, these minerals can be found at like hydrothermal vents, and there's been a lot of discussion if this could be critical to the origins of life. Like, did these minerals create like a gradient that allowed organic compounds to start concentrating? So I guess the original idea was focused more on ocean worlds, but we're going to eventually apply it to Mars. But on ocean worlds, since data latency time is just so long, by the time you get there, start drilling into the ice, and you have your laser underwater, so much time has passed on Earth. So you need quick identification to inform the robot and rover, like, what do you go shoot next? Like, do you keep getting closer? Do you go further away? So it's all kind of just building up to having the rovers or spacecraft decide for itself, like, what needs shot next.
Thanks. I think I saw that you were doing a bunch of sulfides that weren't just purely the iron ones too. So galena I saw on there. And so what was up with those?
Honestly, for galena and sphalerite, we were just kind of trying to like round it out, but we were actually going back and forth with the titles of whether we called it all just like iron minerals or just call it like oxide, hydroxide, sulfide minerals. So it is true, not all of them were iron, but we were trying to like keep the name as simplified as possible.
Okay, Al Imran from JPL once again. Question for Rob. Does that camel method also identify or calculate the ratio spectra of IF? If it does, then how does the denominator of the ratio are calculated? Is that median or just machine learning identification of blend pixel?
Yeah. The ratioing process is actually a pre-processing step for the camel model. We are leveraging the machine learning model published a few years ago by Emmanuel Plabani and Bethany Ellman to identify blend pixels in each column detector to use as denominators to help mitigate noise as well as enhancing the spectral features.
May I ask the question? Yeah. Okay, I have a question for the last but not least speaker. So you mentioned that you applied k-means clustering to all the masks. So what was the procedure? Was it like a greedy, or did you have to tune in for each and every mask?
No, so the k-means step, it's not like the vanilla version of k-means. It's actually like a custom implementation, and we used variants in the output classifications from k-means to determine if we continue clustering. And so it's actually kind of a dynamic algorithm that's able to continue stepping up until we surpass that variance threshold, in which case that's where we step back. And yeah, maybe it wasn't as clear.
Yeah, I have another question for all the speaker. I don't know who will be the best for this, because you guys use machine learning techniques, specifically the k-means clustering. But k-means clustering uses strict segmentation method compared to the other much more like Gaussian based clustering method, for instance, Gaussian mixture model and also DB-scan. So have you tried other method and try to see how those model perform in your study, and what's the accuracy of those models?
Yeah, I guess I can start. When we decided to use k-means, we started with a few clustering algorithms and kind of compared the results to see how they were analyzing the spectra. And we found that k-means tended to produce the results that were most applicable for the application of ROI selection, which is why we inevitably went with that. But yeah, I mean, I think it's very context dependent and dependent on what you're trying to evaluate.
Thank you, and we are exactly on time. So thank you to our first 4 speakers. And we'll invite up the first speaker of our 3rd and final group. Okay, so our the first speaker here is Benjamin Byron, and
all right, yeah, thanks a lot. So yeah, I'm Ben Byron. I'm a postdoc at University of Central Florida. So I'm primarily a lunar scientist, but I'm happy to be here today talking about some Mars rover data, and in particular thinking about how we can apply it to the moon and specifically to the Lunar Vice mission. So first, a little bit of background on Lunar Vice. It stands for the Lunar Vulcan Imaging and Spectroscopy Explorer. So we were selected as part of the NASA PRISM 2 call, and we're going to land on the Gruithuisen domes with a lander and a rover suite. And so these are the Gruithuisen domes here. They're these silicic volcanic features on the near side of the moon. And basically, what we're trying to do is figure out how these things formed, how lunar silicic volcanism forms on the moon in the absence of water and plate tectonics, which is how it was kind of the context that these types of volcanoes form on Earth. But we also have an exploration goal as part of this work, which is to understand the geotechnical properties of the regolith at the Gruithuisen domes. So basically, what are the natural variations of the physical properties, and how do our mission operations affect those properties? So you have a lander that's going to have a plume that could scour the local surface, as well as a rover that will drive over the surface and potentially change those geotechnical properties. And we can use the rover data to understand the geotechnical properties. And an example of that is right here. So previous studies have used essentially visible wavelength images to get at those geotechnical properties. So this is from the LunaCod-1 rover, where you can kind of, you can pull out wheel track depths and use those depths to derive the geotechnical properties such as bearing capacity and cohesion that you're interested in. So we can do this with Lunar Vice. We have a bunch of visible cameras, a visible near-infrared camera on our rover, but potentially we can do even more. So we have a thermal infrared instrument as well called the Compact Infrared Imaging System. So it's co-boresighted with our visible and near-infrared wavelength camera, so we can essentially get both visible and thermal infrared observations at the same time. And so LV-CIRS has 3 spectral channels in the 7 to 8 micron range, which will pull out the composition of the surface, and then a broadband thermal channel from 9 to 14 microns to get at to measure temperatures of the surface. So basically, for Lunar Vice, we're thinking about how can we use LV-CIRS to get at those questions of the regolith properties and how they change during the surface operations. So you can imagine as the rover is driving across the surface, this causes this sort of wheel sinkage, which compacts the regolith, which would then potentially be viewable as a higher thermal inertia in sort of these thermal images that we see. But part of the issue, when we're still a few years away from launch, we're trying to think about operations and stuff for the future, is that there aren't any current or past lunar rover scale thermal infrared instruments that we can compare with. So what we did was think about the great amount of data from all the Mars rovers. So Spirit and Opportunity have the Mini-TESS instrument, which is a hyperspectral thermal infrared instrument. But what we wanted to do was say, okay, well, how does the Martian soil change in the thermal infrared after those interactions? And then also, what strategies can we take from the Mars rovers and think about and apply to our lunar rovers data? So Now some actual data. So this is a PanCam image from Spirit, looking back over the rover wheel tracks, and each of these sort of purple circles is a mini-test observation footprint. And each observation footprint has a corresponding brightness, temperature, and emissivity spectrum to it. So what we did was just look at the wheel track observation, compare it with this undisturbed soil spectrum as well. And this is the brightness temperature for each of those. So the wheel tracks have clearly higher temperature than the undisturbed regolith, potentially due to changes in particle size due to sort of the removal of that Martian airfall dust layer, or potentially some minor effects from compaction due to the wheels as well. If we look at the emissivity spectra, we see differences in emissivity, the real sharp, deep feature here at 12 microns, whereas in the wheel track regolith, the wheel track regolith is sort of this broader, shallower feature, and then there's some differences at sort of these shorter and longer wavelengths as well. So there's clear differences in emissivity there as well. And so this is, again, consistent with sort of changes in the particle size due to, the removal of that Martian airfall dust layer, or even thinking forward, maybe would be more important for the moon than for Mars, is those changes in soil compaction, which can affect the density of the regolith. The next thing we looked at were these Sol 172 to 176 observations. So this was essentially this from Spirit rover. This was sort of parked in one spot and collecting observations of this sort of disturbed regolith and then this undisturbed regolith. And basically this is a whole bunch of different temperatures measured at different times of day over the course of 5 sols. So what we did was just take those temperatures, plot them against local time, and this is what we saw. So the wheel tracks clearly have higher maximum temperature than that undisturbed regolith. Potentially this is due to the changes in albedo. So the wheel tracks have lower albedo, so they could potentially absorb more sunlight and sort of reach those higher temperatures. But it also stays warmer for a lot longer. So this could be due to sort of changes in the thermal inertia particle size, or potentially that density in the upper surface. I will say, though, that we haven't considered the effects of local topography yet. I know that's sort of a really important thing, especially for these types of observations. So we have more thermal modeling to do to kind of confirm this and to rule out those local topographic effects. So short summary of this here was just, we see these changes in the wheel track spectra, which are potentially, changes in grain size or compaction. We see higher temperatures and higher thermal inertia for those wheel track observations than the undisturbed soils. So I am paid by Lunar Vice, so I have to start thinking about how we can, compare this with Lunar Vice. So again, a mini-test is this hyperspectral instrument. The black and the red are those same observations from Sol 45, I think, that I showed before, but these bands are the LV Cirrus wavelength bands. We have these 3 compositional bands around 7 microns, and then this sort of broadband thermal channel here. And so if basically what I did was just say, like, if we had LV Cirrus on the Martian surface collecting these observations, what would it look like? So I just averaged those the mini-test spectra over the LV Cirrus wavelength bands, and this is what we saw. We can definitely see those differences in emissivity at the shorter wavelengths. Probably gets a little bit more complicated at the longer wavelengths there. And if we look at the differences in temperature, again, we have 2 to 3 Kelvin differences in temperature in the Martian data here. Our measurement requirement is 1 Kelvin for LV Cirrus, and we actually potentially expect wider temperature swings for the lunar surface compared to Mars as well. As far as next steps, again, we want to do that thermal modeling to rule out those topographic effects and really, derive thermal inertia for these wheel track spectra. And then I know there's a whole lot of differences between the moon and Mars. The atmosphere is a really big one, differences in temperature swings and types of weathering. And so I know there's a whole lot more stuff we have to consider when we're thinking about directly comparing all of these, but so there's a little bit more work to do there. And I'll end just by saying thanks.
Okay, so next talk by Ali Ittihadi, and the title is Exploring Martian Fracture, a synthesis of geomechanical, mineralogical, and drilling perspective.
Okay, good morning. I'm going to talk about the fracture on Mars. This presentation covers our 3 projects, and they're funded by NASA Peace Corps, and the kind of combination of the geomechanical and the mineralogical and the drilling perspectives on mineral field fracture, specifically calcium sulfate field fracture on Martian surface. So after the quick, the introduction, I'm going to talk about our project, 3 projects, but because of the time limitation, I'm going to share the only specific result and some, the result related to the second project that we are working on it right now. So we know that there are different kind of the veins and fracture on Mars, but we are focusing on the mineral field fractures through our project and studies, and specifically the mechanical properties of the calcium sulfate field fractures that are frequently observed on Martian surface, specifically in Galley crater. So the mechanical properties of these kind of the fractures are so important in terms of the the sampling and getting kind of the intact and safe sample of this kind of the fractures, because these are so important in terms of providing some information related to the Mars history and also, let's say, the microbiological life and existing the water on Mars. So the first project, we characterized the mechanical properties of the analog rocks that hosting the calcium sulfate veins. And it's a kind of the project that consider the mechanical properties of the host rock, the macro scale. So rather than the vein, exactly the vein itself. So, and have a look at the, let's say, the contribution of Mars sample return mission. So this is how we did this study. So we've got, the sample, our analog sample, after collecting these samples from Utah, kind of the formation that is analog to the Martian fractures, and preparing the sample, coring and cutting, and apply the indirect tensile strain test combined with the DIC, the digital image correlation. So this is a kind of the setup, the experimental setup, you can see. And we also, did some sort of the XRD, XRF, and SCM analysis before starting to our experiment. And you can see the sample descriptions in this table. We consider sample without means and with means in different orientation. So these are part of the result for the first project, and you can see the strain map counters during the along with the temperature, along with the fracture, and also you can see the different zone of the fracture propagation, starting from the elastic stage of the crack initiation and the crack propagation. And so these are part of the result. I don't want it to go through the the detail, and also you can see the fracture patterns through our samples, different kind of the patterns. The fracture modes and some sort of the mechanical properties that we find through the first fractures, but for the host rock, mean, it's a kind of the macro scale. So how about the wind, exactly wind? So we need to understand the mechanical properties of the wing itself, and and specifically the bonding. I mean the interface between the wing and the matrix because of the potential mechanical weak zone on that region. So that's why we started to do the second project and have a look at the micro and the nano mechanical properties of the terrestrial analog to the calcium sulfate winds on Mars. So this is the, our methodology that we applied after preparing the sample. Let's say the cutting, crushing, and preparing the specimens, cubic specimens. The samples are subjected to some sort of the microstructural analysis, like the SCM, EDS, and CT scanning and the XRD analysis in the first step. And in the concept of the second step, we did a mechanical test that is the kind of the micro and nano indentation test and scratch test through the beam and also through the matrix and also specifically through the bonding, the interface. So in order to find some sort of the parameters like the fracture toughness and the elastic modulus, indentation map, and the hardness, the measurement. And then at the third step, we also, they did some sort of the again microstructural analysis to understand the microstructural change, if any, and fracture propagation and some sort of the compositional alteration. This is the result related to the SEM, microstructural characterization of our samples. As you can see, we selected different spot, different location on our sample, and you can see the structure and the microstructure of the fracture, and also the matrix and fine-grained cemented sandstone, and also most importantly, you can see the bonding. The interfacial, the zone between the matrix and the fracture, and the gap between these two phases that are so important, and in terms of the mechanical properties, and these are the weak zones. So we need to understand the mechanical properties of these means and matrix, and specifically the bonding and the interface, to be able to ensure the sample integrity and sampling for the Mars sample return mission. So these are the results related to the SCM EDS. So as you can see, the dominant mineralogy related to the vein is gypsum, and also for the matrix, the dominant mineral is the quartz, and we also have some sort of other minerals, albite, dolomite, and also some other minerals. We also, okay, let's go back. And this is the indentation test, and how we apply the indentation test. And these are part of the result related to the indentation test. And we've got the hardness and also the elastic modulus and fracture toughness. So these mean the parameters just gives us some sort of the information and insight into the material's response to the localized stress. So let's go on to the third project. Third project is a little bit different. So it's related to the testing the desiccation crack. So we know that there are some sort of the polygonal desiccation crack on Mars, but the question is, what is the mechanism behind the creation of these kind of the cracks? And this is the setup, and we've got 4 types of the Mars regolith, the analogs, and these are the part of the result. And you can see the pattern, the polygonal pattern, and also some sort of the physical properties of these kind of the polygonal patterns. And these are related to the DIC result, and also you can see the strain counter maps related to the DRT result at different conditions, different temperature, water content, and salinity, and clay content. So let's move on. And for more information, please go through the publications. You can find these publications, specifically that one, how petroleum engineering can help to understand the mysteries of the Martian fractures. Thank you so much. I appreciate for your listening.
Okay, so our next talk by Sean Karneski, and the title is Measuring Bulk Water and Geochemistry for Mars Sample Return with Active Neutron and Gamma Ray Spectroscopy.
Hello, I actually don't know if I know how to. Oh, there it goes. Hi. So I'm going to be talking to you today about some work we've been doing to develop early stages to develop a laboratory technique for the Mars sample return samples. We want to do neutron and gamma ray spectroscopy on the samples, which can get us bulk water and compositional information about the samples. So how do I advance? Oh, the bigger green button. Okay. Okay, so sort of the motivation, why do we want to use this technique on the MSR samples? So there are a bunch of science questions that were identified by the MEPAG working group for science priorities for the sample receiving facility. These two techniques together, neutron and gamma ray spectroscopy, could work towards answering up to 17, maybe more of those questions in conjunction with other techniques or just on their own. These instruments have been used in planetary science for a long time at a wide variety of bodies, including with an active neutron source in the case of the DAN instrument on the Curiosity rover, which is my background. The most important part, which I've highlighted here about these techniques for MSR, is that these techniques can be used while the samples are still in their sealed tubes. We don't need to remove them, so any changes in the hydration state, as soon as you crack open the tube, we can measure the water abundance prior to that occurring. So we have three primary objectives. The current work is simulation work that we hope leads to laboratory experiments to validate these results in the future. But for the simulation side, we want to demonstrate the viability of the technique, show that we can measure the things that we want to measure with these techniques. We want to sort of optimize an experimental geometry before we get into a lab by testing a bunch of different things with our simulations, such as the experiment geometry to maximize our signal and minimize the dose that the sample would receive in doing the measurements. And then we need to address a potential concern, which is to quantify how much neutron capture may be occurring, which could alter isotopes of the sample. So here are on the right a few different cross sections through our simulation space. So the what's labeled horizontal cross section, this is cross section perpendicular to the axis of the sample tube and the axes of the helium-3 neutron detectors. For instance, there's a close-up of the simulated sample tube in the upper right-hand corner. Could use my laser pointer. And then vertical cross section. This shows that our two gamma ray spectrometers. So this simulation code is called MCMP6 Monte Carlo N particle 6 transport code. So it simulates neutron transport histories in a 3D environment. In our simulations, we include a pulse neutron generator, which is this big box here. The sample and sample tube, which is the green, 2 helium-3 neutron detectors that you can see here in this like light blue, 2 high purity germanium gamma ray detectors, which are sort of from this view, sort of one behind the other. You can see them both side by side from this view. The atmosphere that we're using currently is a nitrogen atmosphere. And our most recent simulations were in a simulated stainless steel glove box. But we can test other configurations depending on what the realistic sample receiving facility setup would be. So here's just a couple of results looking at testing different experimental geometries. So the main point of this slide is this plot on the top here. So this is the angle from the source, our pulse neutron generator, to the sample to our neutron detectors. And as you can see, there's a pretty big signal increase of about 33% at an optimal angle that you lose in a forward angle or a backscattering angle, and it really drops off dramatically on the other side. So in our simulations, since we did these tests, this is the angle at which we keep our neutron detectors. You do see that there is some dependence on the angle that we put our gamma ray spectrometer, but the difference here, the y-axis scaling is very different, but the difference here is only about 10%. So we have more freedom in where we put our gamma ray spectrometers with respect to the source and the sample. Okay, so this is our most recent results with variable water abundance. So we keep the same simulation space except for the water that's included in the sample in the simulation. And we varied the water abundance between 0 and 10 weight percent in 0.5 weight percent increments. So these simulations are computationally expensive. So for right now, we've used 1 billion neutron particle histories, which is equivalent to 10 seconds of normal neutron pulsing with a PNG. That's not enough time to get good results. So for right now, we've extrapolated those results out to a point where we get the measurement uncertainty that we would like to have, which I've defined as plus or minus 0.5 weight percent. So in this top plot here, we're looking at those extrapolations from our 10-second results out to further and further measurement times, and the relative uncertainty neutron counts in these experiments would be just statistical uncertainty. So the square root of the counts is your uncertainty. So our relative uncertainty is square root of counts divided by the counts. And as you can see, as you increase your measurement time, your relative uncertainty drops. These vertical lines are the points at which you could distinguish between water values that are 2 weight percent apart, 1.5 weight percent apart, and all the way out to our sort of goal of 0.5 weight percent uncertainty. And as you can see, there's this great diminishing return. So to get even better than this, you'd have to go out to much, much longer measurement times. So this is a plot of our simulations, again, extrapolated from a 10-second simulation out to 5 hours, which is actually a little bit beyond this line here. And as you can see, we have an extremely good correlation between water abundance, which is on the x-axis, and our neutron counts on the y-axis. This is an excellent correlation. And with these relative uncertainties that it appears we can achieve at 5 hours, we get really good separability in our measurements. Okay, so yeah, I think that's that. Okay, so we haven't done as much yet on the gamma ray side, but I have done some initial tests with gamma ray spectrum. These simulations are even more computationally expensive because you have to include electron physics, and in order to get realistic gamma ray spectra. So we do see some features here that are good to see. We see a bunch of oxygen lines. These are actually 3 different oxygen lines with their single and double escape peaks. which is good to see. Our electron physics is working. We also have this 511 keV annihilation line, which is good to see. Our electron physics are working. We have a few elements that have obvious peaks. We also see an iron and aluminum peak that you can't see at this scale. They're not very big. So we're hoping that with greater particle count histories, this was actually generating using 10 to the 8 neutron histories instead of 10 to the 9 like the neutron simulations were. We're hoping that we can identify other elements, and there may be some other techniques, gamma ray spectroscopy techniques that help us pull out more elemental identifications from that side. So on the subject of neutron capture, we're working on currently implementing specific tallies that can tell us exactly how many neutron capture reactions are happening in our simulations. We don't have that up and running yet, but we have some indirect evidence suggesting that neutron capture is very minimal, insignificant. One is adding a tally around the sample tube itself to count how many thermal neutrons, which are the neutrons that are most likely to be captured, that pass in and out of the sample tube. And in this set of simulations on the 10 to the 8, am I out of time? Okay. Can ask questions about thermal neutron capture. And I'll just leave my conclusions up. Thank you.
All right. So we have our last speaker for the session, Eduardo Martinez, speaking about analyzing phosphate absorption behavior on Mars analog clay mineral, experimental and modeling approaches to assessing biosignature potential.
Hello, everyone. My name is Eduardo Martinez. I am a second-year PhD student under the advisement of Dr. Hausrath. And yeah, I am here to talk to you about how we can use phosphate as a potential biosignature. And so just to establish a little bit of context about the presence of phosphate on Mars, we know that it is present via its detection in Martian meteorites and by orbiter and rover data. And so we know that samples are currently being cached and collected and cached on Mars to be returned to Earth. So we can potentially analyze the phosphate content of those samples. And so as many of you may know, the location of these samples is from Jezero Crater, which used to be a former Delta Lake system, which has a really high potential for life to have occurred. And so if we're looking at biologic phosphate, then we know that phosphate is heavily biologically cycled on Earth. And so we can use that as a potential signature via its oxygen isotopes. And so I want to bring your attention to this graph where we have some phosphate, the composition of the oxygen isotopes in phosphate and water from Martian meteorites. And I want to first start with the bottom plot, which is the Mars baseline water. So here we have a delta 18 of the water in Northwest Africa 7034, which is around -5 per mil. And then if we move up, we have an abiotic baseline, which is coming from the phosphates in Shergottites, Northwest Africa 7533 and Allen Hills 84001. And so we can use this information from these igneous minerals because they are essentially less enriched in delta 18 or the less heavier isotope. And so here we have some data or estimated or calculated values from the oxygen isotope composition of phosphate in equilibrium with the oxygen isotope composition of water of Northwest Africa 7034 at different temperatures. And so what we're looking for as a signature is essentially the shift from the baseline equilibrium composition. So here, if we fall in the higher range of the oxygen isotopes, we can use the secondary or adsorbed phosphate that is not in equilibrium with the baseline of the abiotic baseline due to biological exchange. And then a second potential measurement that we can be making is the delta 18 in secondary minerals or adsorbed phosphate that is in equilibrium with the oxygen isotopes in water. And so that is also due to biological exchange. And as you can see, these values lie in a more enriched delta oxygen 18 And so both of these measurements are able to be distinguished from the abiotic baseline. And so that's essentially what we're looking for. And so that brings us to our objective and our research question, which is, would we be able to detect the if we would be able to detect our biologically cycled phosphate, or would it be obscured by the oxygen isotopes of abiotically cycled phosphate? And so we will be doing a model to investigate these parameters, which include adsorbed phosphate onto clay minerals, microbial phosphate uptake and decay, precipitation and dissolution of phosphate minerals, and hydrolysis of phosphorus-containing organics. And the figure on the right is just a graphical representation of where we might have a high potential biosignature. And that is when we have a high concentration of cells, a relatively low dissolved phosphate concentration, and opposite of that, where we might have a low biosignature potential, and that is when we have a low concentration of cells, a lot of dissolved phosphate, and a lot of hydrolysis of phosphorus-containing organics. And so if we fall within this upper range, then we might be able to have a stronger signal of these isotopes. And so that brings us to our follow-up question about how we can apply this to the Mars 2020 samples, and that is asking if can we use a composition of the Mars 2020 samples to assess their promise of using this potential biosignature. And so to do this model, we are using Stella Architect, which is a system dynamics modeling, which allows us to use a stock reservoir where we are able to measure the accumulation of phosphate. You can think of this as a tub of water filling with water. You could think of your next parameter, which is your flow, as a flow rate. You could think of this as a valve that's filling your pool. And then your converter where you have your functions, your variables or your constants, and then you have your information flow, which you are able to direct your functions, your flow rate, and your stocks or reservoirs. And so here's just a simple image of what we are trying to produce, which is this schematic is the accumulation of population, and that is dependent on these valves, which is births and deaths, and that is a function of the birth rate and the death rate. And so just like with any model, we have to come up with some assumptions. And some of the assumptions that we're looking for this work and for this particular initial run of the model, we are using phosphate adsorbed into irisaponite, and that is from experimental sorption data, which is my chapter 1 of my dissertation. We're using Geobacter metalloreducens, which is a Mars-relevant microbe that is limited by iron. And then we have apatite, which is limited by kinetics. And then we are able to establish a control boundary. And so I just want to kind of give you the idea behind this. So if we establish a control boundary from this figure from Pixel, where we have phosphate minerals alongside with other minerals, but we apply a hypothetical microbial population if we add aqueous phosphate and then adsorbed phosphate. And as you can see, they all have fluxes between each other. And so we have phosphate from minerals at this moment coming in or having an infinite phosphate mineral for this particular run. And so to continue the methodology, we're using some ordinary differential equations to solve for this. And so the equation on the right is the bacterial growth and decay, and that is a logistic growth curve, which is dependent on an initial microbial population growth rate via the monod growth rate, our carrying capacity, and then the equation on the right is our change in concentration over the change in time, and that is a function of the mineral concentration, the reverse reaction rate, and the forward reaction rate, and then adsorbed concentration and the desorbed concentration. And so that brings us to our model, and this is this is in the initial stages, so I'm still working on optimizing this model, but I kind of want to just show you how what this may look like. Here we have our dissolved phosphate mass, which is decreasing as microbial population is increasing and our adsorbed phosphate is increasing. And here you have your aqueous phosphate, you have your biologic phosphate, you have your sorbed phosphate, and then here you have our mineral phosphate slowly dissolving and adding to our pool of aqueous phosphate. And so with that, I just want to reiterate that this is an initial model and I'm still working to optimize it. But with this model, we are able to model the phosphate distribution between different phosphate pools. And this allows for the assessment of the potential to detect the isotopic signature if life were present under different conditions. And then I'm still working on refining the inputs and calibrating our model to allow for more constraints of this potential biosignature. And I kind of just want to come back to this figure where we are looking at the measurements of the isotopes and see if any of these models or any of these samples or trying to identify which of these samples have a high potential of this biosignature. And so with that, I want to acknowledge NASA, our funding grant, our collaborators, and the House Brass Lab for all their support. And with that, thank you, and I'll be happy to answer any questions.
Well, thank you for that. And that was the end of our final four. And now if the last four speakers can come up to the front so we can have our final Q&A of the conference. And remember, if you're asking a question, then you state your name and affiliation.
Hi, Ari Essenfeld from Los Alamos National Lab. Thanks all for the talks. My question is for Sean. Going back to that slide where you had the two scatter plots, one on the bottom was showing angle, the x-axis was angle and the y-axis was like the signal strength or something for the neutron, the nuclear spectrometer and the gamma spectrometer, if I remember correctly. I was wondering, it looked pretty smooth to be increasing monotonically for the upper plot up to 120 degrees and then a steep drop off, also monotonic at that point. Whereas with the gamma, it was a little more variable. And I was wondering if you could talk a little about why it would go up and down with angle for the lower plot.
I did less analysis of the results from the gamma ray spectrometer. For the neutron one, I specifically looked at the difference in signal with a sample present versus not present, so I could get an idea of which counts were coming from the sample and how that varied. For the gamma ray spectrometer, by the time I got there, we're very limited on space around the sample, and I really needed to make sure that we had maximum neutron signal. So the gamma ray was just to make sure that we weren't going to get like an order of magnitude different counts in one position versus another. So it's actually in the current simulations, it's actually based on that plot, the worst spot, the lowest signal spot, because that's the position that remains around the sample. I think that slope is probably primarily due to proximity to the source, actually, rather than the angle away from the sample. But yeah, I'm not completely sure the character, the like smaller scale character within that overall decreasing slope. I'm not entirely sure.
Thanks for that info. Thanks so much.
Hi, I'm Alan Treeman, Lunar and Planet Changes. A couple questions for Mr. Martinez. Your model starts with apatite as the beginning phosphate. I'm wondering if you can adjust it for others, because the image you showed from the pixel thing, I think that one has vivianite in it rather than apatite. And that sort of goes to the second question. I didn't notice if your model includes for precipitation of phosphate minerals also. I mean, you're putting in an iron smectite, and if you got phosphate, you might well precipitate vivianite or other iron phosphates out. Thank you.
Yes, I will be considering all those minerals. Right now, I'm actually collecting all the like dissolution rates, mineralization rates, and yeah, I still have to iterate through different types of the minerals that we have, and I believe that I should add iron as a stock because I do accumulate, and that is also limiting my bacterial growth, so that changes over time. So yeah, I'm still working with trying to incorporate more minerals, more bacteria, more types of bacteria, and yeah, more parameters. But yes, thank you for that.
Steve FASU, question for Ben and then one for Sean. Ben, you already said that it's unlike there's no equivalent airfall dust on the moon. So that whole sort of layer version of Mars will not be present. But what's interesting, you showed images from rover tracks from, I think, the Chinese rover and then Lunicod. And one of them, the Chinese rover, clearly showed a change in apparent albedo, anyway, in the tracks versus the surroundings. And I thought the Lunicod one sort of didn't show a real obvious albedo variation. I'm wondering if literally the wheel design, the churning of this material in the lunar regolith based on how the wheel interacts is creating maybe a fluffier version that maybe we're actually seeing shadowing. So I wonder if you're, and by the way, do you know what the it's Vice rover, what's the name, what the wheels will be like on that? So I'm just thinking about wheel design and the interaction and how that's going to influence apparent albedo, for example.
Yeah, that's a good point. So Lunar Vice, we just had our lander and rover provider selected. I as far as I know, we don't know the specific design of our wheels yet. Yeah, it's a good point. So I know there is ongoing work at UCF and at Exolith Labs to kind of to measure changes in like lunar simulant reflectance properties as a result of wheel passes, and that's sort of just ongoing work. Preliminary work is kind of showing there's not much change in albedo. I think we were, the wheel that was being used was, I don't want to say which one was that because I can't remember, but it was one of the potential future lunar LTV wheels or something like that. But yeah, I think initial results showed that maybe there weren't changes in reflectance as a result of that specific wheel. That's a good point though, because yeah, depending on the design of the wheel, some parts of the track can get compacted and some parts can kind of get fluffed up a little bit if there's sort of grouser tracks that can kind of do that. And actually we had an undergrad, Abigail Glover, working on something like that recently as well. She had a poster last night where again, kind of seeing how those differences in the different parts of the wheel track look in reflectance, and we're starting to look at thermal properties as well. So there's a lot of work still being done, but I think preliminary work, at least in simulant test beds, shows not much change in reflectance. So yeah, I'm not sure. Yeah, the Lunicod, it was kind of hard to tell differences in reflectance, but it did seem pretty clear in the Changi tracks. So yeah, I guess I don't have a really good answer for you, but it's sort of ongoing work.
Cool. And Sean, I'm wondering about H2O in a vapor phase inside the tubes, as opposed to bound in minerals or in the rock.
Sorry, can you move a little bit closer
Sorry.
to the mic?
Yeah.
Loud.
Yeah. Can you detect H2O in the vapor phase inside these tubes, or are you and really it's hydrogen, right? Obviously, but can you see hydrogen in the vapor phase in the headspace, of these tubes versus only bound up in minerals? Because to me, that would be an interesting, once these things get open, and we've been told that there's no elegant design for preserving, they're going to have their best effort to preserve the headspace stuff. But if you can learn ahead of time something about the vapor phase hydrogen, I think that would be useful.
Yeah, so the technique is sensitive to hydrogen in any form. So we cannot distinguish between vapor phase and H2O or OH locked in a mineral, for instance. We could do, some post-processing of measurements that are done on like the hard rock or soil after it's out, the relative hydration of that versus what we measured. And that might give us some, I don't know what the uncertainty would be on the water vapor in the headspace. But yeah, we're sensitive to all hydrogen in the sample tube. And with these measurements, given the very small volume of the samples, and this is a volumetric technique, getting any kind of more specific measure from like one end of the sample tube or something is probably not something we could do very well. We're gonna get a bulk water abundance or a bulk elemental composition from the GRS.
And doesn't your modeling depend on the density of the, and like, in a vapor phase, obviously it's much less dense. Doesn't your modeling depend on the density?
Yeah, the density is a parameter that would affect the results that we get. That's something that we could figure out after the fact, though, and run more models. As long as we have the data from prior to opening the sample tubes, then we can correct for anything like that where we made wrong assumptions about density, for instance.
So you measure it and figure it out later.
Yeah.
Right. Thanks.
Jeff Johnson, APL, question and a comment for Ben. First, a comment in response to your discussion with Steve. What we see a lot of times with the tracks on the Mars rovers is that it's very lighting angle dependent in terms of how the flattest part might be really shiny when you're looking at high phase angles versus not. So that's something to consider for the work you were talking about. The other question I had was whether or not you've included in your plans some laboratory analyses where you can do things like look at disturbed and undisturbed materials. There's some literature, I can send you something where we did that in the field a long time ago, and that might help if you're doing it with linear simulants, for example.
Yeah, that's a really good point. So again, Exolith Labs is this group associated with UCF that has, that creates these simulants, and they have these regolith test beds that we've done some preliminary tests, but I think, you're right. We should plan on doing some more detailed tests, out there as well. So I think that's a really good suggestion.
Yeah, more than just with, the wheels you think you'll use, but just, doing it on your own, just tamp something down and,
Yeah. So just fluffed up versus kind of compacted.
Yeah.
That's a good point. We've also, I think we can definitely do that. We've also considered trying to incorporate, thermocouples and, different types of thermal observations in this as well. So, it's slightly different, for vacuum on the moon versus in a lab, but I think that's a really good point. Great.
Alan Treeman again. This is for Dr. Zarnecki about the neutrons. It's of course important to know the bulk hydrogen content, but as a geologist, I'd sort of like to know where it's concentrated in the sample. And so my question is whether neutron tomography can be done with a pulse neutron generator, whether there's any hope of localizing the hydrogen in the sample while it's still in the tube.
So I think we would very quickly, with a technique like that, run into a problem of activating a sample potentially, which would be presumably a no-go from the Mars sample community. But I haven't looked into it. What fluxes, what dose rates would be required. I don't think that that's done with a PNG. I think you would need like a neutron beam or something.
And that was sort of the question. I've done neutron tomography with a reactor generator, which is make it a little more difficult for the sample receiving facility than a PNG. And so that was a question whether it would be possible with something that would fit in a sample receiving facility. And there is activation. There's activation no matter what you're to when you aim neutrons at it. A second question would be whether PNG, the dose of neutrons from PNG, is going to affect the organic content, the organic materials in any return sample.
Yeah, we haven't been able to look too much into that. That's not something that we can simulate well in the current simulation. So that would involve additional work. But my immediate reaction to that question is, I think that we are going to be irradiating the sample much, much less than what it's experienced at the surface of Mars, and in transport back to Earth in, interplanetary space. But actually looking at relative numbers, haven't done yet.
From JPL, I have a question for Ali. So, can you give me an idea about like the sizes of polygonal cracks and fracture? Are those measurable, and what's the dimension of those?
Yes, this is a part of our third project, and we did kind of the desiccation test, and this kind of the fractures are polygonal, are regular hexagonal shape, and these are, I mean, the kind of the, let's say the length of them is about the 10 centimeter or something like this. So these are so similar to the polygonal cracks on Mars that we are observing right now. I mean, so the mechanism behind the creation of this kind of the cracks, there are lots of the theories, but we did the desiccation, and this is the most likely, I mean, the theory behind and the mechanism behind the creation of this kind of the crack.
Yes, I have a question for Sean. You asked us to ask you a question on neutron capture. Would you like to fill us in on what you missed in the end of your talk there?
Yeah, thank you. Sorry for running over time. But yeah, essentially we right now we have two sort of indirect measures suggesting that neutron capture is extremely minimal. One is what I started to describe with putting a tally of thermal neutrons, which are the primary culprits in neutron capture, putting that tally directly on the neutron sample tube surface in the simulation. So it tallies any thermal energy neutron which is passing through the sample tube. And in a simulation of 10 to the 8 neutron histories, there were less than 10, like 10 thermal neutrons that pass through the sample tube, indicating that there's very, very, very minor neutron thermalization, which should also lead to very minor neutron capture and isotopic changes related to that. The other indirect measure was the time stamping that we did on the gamma ray spectrometer in those initial tests. Those were also 10 to the 8 neutron history simulations. And we recorded 0 gamma rays in what I've seen in literature described as the thermal neutron capture time window. So essentially takes a while for a neutron to thermalize in the sample. And so gamma rays that result from that capture appear later in your detector than gamma rays that are generated by neutron scattering reactions. So the spectrum that I showed, all the gamma rays in that spectrum are due to inelastic scattering of neutrons in the sample rather than neutron capture. Neither of those are slam dunks. We know exactly how much neutron capture is occurring, that it requires a more advanced tally that we're working to implement in the simulations for like the next round. Thank you for asking.
Rob Platt from Imperial College. Question for Eduardo. Can you expand a bit more on why you chose the particular microbe you did for the experiment? I think you said it was Fe limited.
Yes, so it's Mars relevant in that it uses iron for its metabolism. And so we are considering other microbes like another Geobacter sulfur reducens and Schwannella wendosis, which our lab works with. But I think for I guess this initial model run that I'm still trying to work on is was kind of just I found a lot of the values in literature that were applicable to some of the how do I say this applicable to our work. And so yeah, I think there are other cultures that or other microorganisms that we can use. Yeah, that's still a work in progress to identify more.
In the last 30 seconds, the left of our session, I'd like to thank our speakers, the four from the final one, and everyone from the entire group and our audience. And hope everyone's had an awesome LPSC, and hopefully see you again somewhere next year. And if you missed anything from one of the talks, you can always look at them, at least always in the next 30 days, look at them if you're a registrant for this conference online.